When I was a boy, I spent all my spare time searching through rocks in places like this. Over time, I began to learn something about the Earth's evolutionary history. By and large, it's a story of slow, steady change.
In the beginning, before there were planets, oceans, or even the faintest spark of life, there was only a quiet cloud of gas and dust drifting through the darkness of our galaxy. A cold and silent nebula made of hydrogen, helium, and the scattered ashes of ancient stars. It floated for millions of years, undisturbed, until something changed. Perhaps the passing arm of the Milky Way compressed it. Perhaps a nearby supernova sent shockwaves rippling through space. Whatever the trigger, the effect was profound. Gravity began to pull the nebula inward, slowly at first, then with increasing force, drawing the cloud into a tight, spiraling collapse. This was the beginning of the Sun, and with it, the beginning of Earth. As the nebula contracted, particles collided, releasing heat at the center of this swirling cloud. Mass accumulated, forming a dense and warming core. Over time, this core grew hotter and heavier. Pressure increased until hydrogen atoms fused into helium, igniting the fire of nuclear fusion. The light switched on. The Sun was born. Its brilliance flooded the nebula, clearing out leftover gas and setting the stage for the formation of planets. Around the newborn Sun, a disk of debris took shape. Astronomers call it the protoplanetary disk. To the early universe, it would have looked like a glowing ring of dust, rotating slowly, holding within it the ingredients of future worlds. Dust grains, no larger than smoke particles, drifted through this disk. When they collided, they stuck together through electrostatic forces. At first, these collisions were gentle, almost delicate, but over tens of thousands of years, these specks gathered into larger clumps. Millimeter grains became pebbles. Pebbles became stones. Stones became boulders. Slowly, the architecture of a planet began to emerge. Gravity, even in its weakest forms, is endlessly persistent. Once a clump grew large enough, its gravity pulled in more material. These growing bodies, called planetesimals, orbited the young Sun in chaotic paths. They crashed into one another, fused, fragmented, and fused again. Each collision released heat, melting parts of their surfaces. In these moments, chemistry began to change. Metals separated from silicates. Molten cores formed within the larger bodies. The early solar system was a violent place, ruled by impacts and constant rearrangement. Earth's story began with one of these planetesimals. It was not yet the blue world we know. It had no oceans, no continents, and no atmosphere. It was simply a growing sphere of hot rock pulled together through relentless collisions. As it expanded, gravity became stronger, drawing in more material from the disk. Millions of impacts sculpted its surface. Some were small and barely noticeable on a planetary scale. Others were catastrophic, releasing enough energy to vaporize rock and reshape the planet entirely. Although we imagine planets as stable and solid, the early Earth was anything but. Its surface was molten, forming vast oceans of magma. The heat came from three sources: leftover energy from its formation, the constant rain of impacts, and the decay of radioactive elements buried within. Together, they kept the young planet glowing like an ember in the cosmic dark. While Earth was forming, so were the other planets. Closer to the Sun, Mercury and Venus grew in similar ways, though each developed a different fate. Farther out, the gas giants accumulated enormous atmospheres. But Earth remained in a delicate balance, close enough to receive warmth, but far enough to avoid vaporizing entirely. It was positioned in a region scientists call the habitable zone. At this stage, habitability was a distant promise, not a reality. Yet, the conditions for a future life-bearing world were beginning to take shape. In the swirling disk, turbulence sculpted rings of material. These rings fed the growing planets. Within Earth's ring, icy bodies from the outer solar system occasionally plummeted inward, delivering water in the form of vapor and frozen minerals. Long before oceans existed, the ingredients of water were already being incorporated into Earth's interior. As Earth grew, gravitational interactions altered the orbits of surrounding planetesimals. Many were pulled inward and collided with the forming planet. Others were ejected outward. But one collision would change everything: the impact that formed the Moon. Before that event, Earth was still incomplete, still undergoing the final stages of assembly. In the early solar system, instability was a natural state. Multiple planetary embryos, some as large as Mars, were moving through intersecting orbits. One such object, often referred to as Theia, existed near Earth's orbital path. Over time, gravitational forces nudged their trajectories closer. The solar system did not yet have the quiet predictability we see today. Theia and Earth were on a collision course, though it would take millions of years before their paths finally crossed. Meanwhile, Earth's accretion continued. Each new impact brought fresh material, metals, silicates, gases, all mixing into its growing mass. Its interior was now layering. Dense iron and nickel sank toward the center, forming the core. Lighter materials rose toward the mantle and crust. The dynamo that would one day create Earth's magnetic field was beginning to stir. This field would eventually protect the planet from solar winds and radiation, making it more hospitable for life. But at this early stage, the field was still weak, fluctuating unpredictably. The formation of the Sun also played a critical role in shaping Earth. In its youth, the Sun was far more active than it is today. It emitted powerful solar winds, streams of charged particles that swept across the solar system. These winds blew away much of the remaining gas in the protoplanetary disk. They also stripped atmospheres from many small bodies. Early Earth's first atmosphere, mainly hydrogen and helium, was likely blown into space. Yet this loss would become a necessary step for the formation of a second, more stable atmosphere produced by volcanic outgassing later in Earth's history. As the solar winds cleared the disk, the era of planet formation began to slow. Fewer collisions occurred. The environment stabilized. Earth had become a roughly spherical planet with a molten surface. Its interior churned with heat. Its exterior glowed with incandescent lava. Though destructive, this period was essential. The molten surface allowed heavy metals to sink and lighter silicates to rise, creating internal structure. Differentiation, as scientists call it, is a key process in forming planets capable of supporting complex geology. The solar system was now taking recognizable form. Jupiter, the giant, dominated the outer regions. Its immense gravity influenced the movement of countless objects, shaping the asteroid belt and protecting the inner planets from excessive bombardment. Mars formed smaller than Earth due to Jupiter's gravitational interference. Venus became similar in size but followed a different evolutionary path. Earth occupied the middle ground, a place of balance. Meanwhile, the planet continued to cool slowly. The surface began forming a thin crust, though impacts frequently shattered it. Beneath the crust, magma surged upward in plumes. Volcanic activity was immense. Gases trapped in Earth's interior, water vapor, carbon dioxide, nitrogen, sulfur, were gradually released into the sky. These gases formed Earth's second atmosphere, far thicker and more hostile than today's. Yet this atmosphere would eventually lay the foundation for life. In the silence of space, Earth rotated rapidly, completing a day in only a few hours. The Moon, after its formation, would slow this rotation, but that moment had not yet arrived. The young planet spun with tremendous speed, generating strong atmospheric currents and violent storms across its molten landscape. Lightning arced through the thick clouds, contributing to chemical reactions that would later be important for organic molecules. But for now, Earth remained barren. Still, change was constant. The solar system was evolving alongside it. Comets, made of ice and rock, continued to bombard the inner planets. These icy visitors contributed water and other volatile compounds. Although the source of Earth's water remains debated, many scientists believe a significant portion arrived during this period through millions of impacts, droplets of water mixed into the crust and mantle. Once the planet cooled enough, this water would eventually rise to the surface, creating the oceans. As the bombardment slowed, the sun's brightness increased. Young stars brighten gradually as they age, and the sun was no exception. The increase in energy began to influence Earth's climate. Though still molten in many places, some regions started to solidify. A more permanent crust formed, though it remained thin and unstable. Tectonic processes were beginning, driven by internal heat. The groundwork for future continents was being laid deep within the planet. Though we often think of planets as forming quickly, Earth's birth required tens of millions of years. The timeline is immense. Yet, in cosmic terms, it was rapid. From a cloud of dust to a glowing molten sphere, Earth's transformation was guided by physics, chemistry, and gravity. Each step brought it closer to becoming a world. Then came Theia. The collision itself belongs to the next outline, but its approach was already influencing Earth's orbit. Gravitational interactions destabilized both bodies. Their paths spiraled toward each other. Soon, the impact would reshape Earth forever, giving rise to the Moon and altering the rotation, tilt, and internal structure of the planet. It would be the final major event of Earth's formation. And so, the stage was set. The sun burned steadily at the center of the new solar system. The planets orbited in their new paths. Earth, still young and molten, awaited the collision that would transform it. What began as dust in a collapsing nebula had become the foundation for a future world. A world that would one day host oceans, continents, forests, and life in all its diversity. The birth of Earth is not just a geological story, but a cosmic one. It reminds us that everything around us, the air we breathe, the ground beneath our feet, the water we drink, even our own bodies began as particles drifting in the dark arms of the Milky Way. Through gravity, heat, and time, these particles assembled into a planet unique in the solar system. The journey from stardust to world was long, violent, and beautiful. Earth's story has only just begun. Earth, newly formed from collisions and cosmic debris, was still far from the stable, life-bearing world we know today. In this early chapter, the planet existed as a seething, violent sphere wrapped in fire and chaos. The surface churned with molten rock, the interior boiled with radioactive heat, and the sky was nothing like the blue dome we see now. Instead, thick clouds of vapor, dust, and volcanic gases swirled into a dark and alien atmosphere. Lightning ripped through the sky constantly, illuminating a world dominated by destruction and transformation. This period is known as the Hadean Eon, named after Hades, the ancient realm of fire, and the name is appropriate. Earth's surface was a global magma ocean. Continents did not exist. Oceans had not yet formed. The crust was thin, fragile, and constantly broken by impacts. Volcanoes erupted across the entire surface, releasing immense plumes of gas and lava. The atmosphere was thick with carbon dioxide, nitrogen, sulfur compounds, and water vapor. No oxygen, no stable climate, and no conditions suitable for life. But despite this hostility, the groundwork for everything that would come later was being built. The young sun shone dimmer than it does today. It emitted strong solar winds, powerful enough to strip away the first atmosphere Earth had briefly held. This early atmosphere likely consisted of hydrogen and helium, remnants from the solar nebula, but these light gases were blown into space by the newborn star's radiation. This loss created room for a second atmosphere, one that would form from volcanic outgassing and cometary impacts. Earth's formation had generated enormous heat. Gravitational compression, radioactive decay, and the energy from countless collisions kept the interior molten. Within the planet, heavier elements like iron and nickel sank inward, forming the core. Lighter silicates rose to form the mantle. This differentiation released even more heat, contributing to convection currents deep within. These currents would eventually drive plate tectonics, but in the Hadean, the crust was far too unstable for organized plates. Instead, the surface constantly melted and reformed, never remaining still long enough to build lasting geological features. Comets and asteroids still bombarded the planet regularly. Though the heaviest phase of accretion was ending, the solar system remained crowded with debris. Each impact tore open the crust, ejecting molten rock into space and reshaping the surface. Some impacts vaporized entire regions, sending shockwaves across the planet. Others delivered new materials, including water-rich minerals that would play a crucial role in Earth's future oceans. But at this stage, the planet could not hold liquid water. The surface was too hot, and any water instantly evaporated, joining the thick, steaming atmosphere. Volcanic activity was ceaseless. The mantle churned beneath the thin crust, pushing magma upward in colossal floods. Volcanic gases filled the atmosphere with carbon dioxide and water vapor, creating an early greenhouse effect. Without this, Earth may have remained frozen once it cooled, since the young sun emitted less heat than today. Instead, the greenhouse atmosphere trapped warmth, keeping the surface extremely hot but dynamically evolving. Lightning storms were constant. Charged particles in the dense atmosphere created electrical imbalances, producing frequent strikes across the molten landscape. These storms may have contributed to early organic chemistry, though life was still far in the future. For now, these reactions were simply chemical experiments occurring in a hostile environment. The sky, thick with ash and gases, glowed red and orange from the reflection of molten lava. The horizon flickered with eruptions. Meteor trails cut through the atmosphere, leaving brief streaks of fire before exploding on impact. Each collision added to the intense heat. The crust, already fragile, often collapsed back into the mantle, recycling newly formed minerals and preventing the permanent creation of continental rock. In this dynamic world, nothing lasted long. Beneath the surface, the core continued to form. The inner core became solid, while the outer core remained liquid. This layered structure created the beginnings of Earth's magnetic field. Though weak at first, the field was crucial. It began protecting Earth from some of the sun's harsh radiation, preventing complete atmospheric loss. Without this magnetic shield, Earth might have ended up like Mars, stripped of its atmosphere and oceans. But even in this early stage, the seeds of protection were taking shape. The violent conditions of early Earth were not unique. Other planets in the solar system also experienced early bombardment and volcanic activity. But Earth held a special balance of mass, composition, and distance from the Sun. This allowed it to retain heat long enough to form a magnetic field, but not so much that it became a perpetual magma world like Venus. It retained volatiles like water, carbon, and nitrogen, while still avoiding the fate of gas giants. This balance would prove essential in the coming eons. As millions of years passed, the intensity of impacts gradually decreased. Large planetesimals were now rare. The crust began to cool slightly, forming thicker patches of solid rock. Though still unstable, these early proto-continents represented the first steps toward a more structured surface. Volcanic activity provided fresh minerals and gases, building a complex chemical environment. During this time, gases released from volcanoes formed what scientists call Earth's second atmosphere. It consisted mostly of carbon dioxide, with smaller amounts of nitrogen, methane, hydrogen sulfide, and ammonia. Water vapor was abundant, creating a thick, humid blanket around the planet. When Earth finally cooled enough, this vapor would condense into rain, but that moment was still far away. The Hadean world was shaped by energy in every form: heat from the interior, radiation from the sun, kinetic energy from impacts, and electrical energy from storms. These forces constantly sculpted the surface and atmosphere, ensuring that Earth remained dynamic. This energetic environment allowed complex chemical reactions to occur, setting the stage for the emergence of life much later. But at this stage, the planet was entirely barren. Deep within the mantle, convection currents shifted molten rock. These currents caused sections of the early crust to break apart and collide. Some regions thicker than others may have briefly existed as proto-continents, only to be melted down again by new impacts or massive volcanic eruptions. This recycling of crustal material enriched the mantle with minerals that would later fuel plate tectonics and continental growth. Temperatures at the surface remained extreme, likely above 1000 degrees Celsius. No liquid water could exist. The atmosphere was a toxic mixture of gases, unbreathable and dense. Yet, the greenhouse effect kept the planet from cooling too quickly. If Earth had cooled too fast, it might have become a frozen world, unable to support later evolution. Instead, the violent heat allowed the geological engine to stay active. During this era, a major event loomed on the horizon: the giant impact with Theia. This Mars-sized body had formed near Earth's orbit and drifted gradually into a crossing path. As Earth grew heavier, its gravity influenced Theia's movement. The two bodies slowly approached a catastrophic collision.
Though the impact belongs to the next chapter, its effects on Earth's environment were already building. Gravitational disturbances may have created additional impacts from smaller bodies.
The system was becoming increasingly unstable. Meanwhile, the atmosphere grew thicker with volcanic gases. Infrared radiation from the hot surface was trapped within this dense gas layer, slowing, cooling, and maintaining the molten state longer than expected. The oceans of magma beneath the crust moved in waves, forming and collapsing mountains of molten rock. These flows shaped the early topography, smoothing some regions and raising others. As the crust cooled slightly over time, chemical differentiation began. Minerals with higher melting points crystallized first, forming a primitive crust. Lighter minerals, especially silicates, floated upward, forming the earliest felsic rocks. These rocks were the ancestors of modern continental crust. Though most have long since been destroyed, small traces preserved in ancient zircon crystals reveal that Earth may have formed stable crust earlier than once believed. In this harsh world, the foundations of future oceans were forming in the atmosphere. Vast amounts of water vapor circulated above the molten surface. Storms raged for centuries without pause, driven by the extreme temperature differences between the surface and upper atmosphere. When the planet finally cooled to below the boiling point of water, this vapor would condense, falling as rain for millions of years. These storms would fill the first ancient oceans. But during the Hadean, the world remained too hot for that transformation. The pressure of the atmosphere prevented condensation, keeping water in vapor form. Yet the water collected in the atmosphere signaled what Earth would one day become a water-rich planet, unlike any other in the inner solar system. The Hadean Eon lasted hundreds of millions of years. Throughout this time, the planet underwent constant restructuring. Even the rotation of Earth changed. Early Earth spun faster, completing a rotation in roughly 6 hours. Over time, tidal interactions with the Moon, once it formed, would slow this rotation to the 24-hour cycle we experience today. But in the Hadean, the rapid spin contributed to atmospheric turbulence and extreme weather conditions. Chemical processes also began to establish the building blocks of future life. Volcanic vents released gases that reacted in the atmosphere. Ultraviolet radiation from the sun broke molecules apart, allowing them to recombine in new ways. Lightning provided additional energy for molecular transformations. Though no living organisms existed, Earth was becoming a chemically rich environment with increasing complexity. Beneath the surface, the core continued to grow solid. This inner core formation strengthened the magnetic field, gradually expanding its protective influence. A stable magnetic field is one of the most important features for maintaining life. It deflects harmful solar radiation and preserves the atmosphere. Though still weaker than today's field, the early magnetic bubble helped shield the developing planet during its most vulnerable phase. Earth continued to cool, but slowly. The crust thickened slightly. Some regions may have solidified entirely, forming the first long-lasting pieces of crust. These fragments drifted upon the mantle, carried by convection currents. This movement resembled an early version of plate tectonics, though far more chaotic and less organized. These floating fragments were the seeds of future continents. Through all this chaos, Earth edged closer to the moment that would define its future. Theia approached, pulled by gravitational forces into Earth's path. The impact would obliterate the early crust, reshape the interior, and form the Moon. But even before that moment, Earth's violent beginnings had already set the stage. It had formed a core, a mantle, a crust, and an atmosphere. It had accumulated water and volatile compounds. It had built internal heat engines and magnetic protection. It had survived a storm of cosmic impacts. What emerged from this turmoil was a planet ready for transformation. The Hadean world was not calm or gentle, but it was essential. This violence carved the framework upon which oceans, continents, life, and ecosystems would one day flourish. The newborn Earth was a world of fire, storms, and constant change, but within this chaos lay the hidden blueprint of everything that would follow. Earth's violent beginnings were only a prelude to the most defining event in its early history. Out of all the collisions, out of all the impacts that shaped the young planet, one stood apart in scale, consequence, and cosmic importance. It involved a planetary body, roughly the size of Mars, now known as Theia. This collision would forever change Earth's rotation, tilt, internal structure, and even its destiny as a life-bearing world. It would give birth to the Moon, reshape the atmosphere, and ignite geological forces that persist to this day. Without this single event, Earth would be unrecognizable, perhaps uninhabitable. Theia itself formed in the same protoplanetary disk as Earth, near the region of the inner solar system. Like Earth, it grew from dust, rocks, and molten material drawn together by gravity. For millions of years, Theia likely orbited close to Earth's path. Both worlds grew larger, their gravitational influence expanding. But planetary orbits during this era were unstable, influenced by countless interactions among forming planets and debris. Eventually, Theia's orbit began to intersect Earth's. The two bodies slowly drifted toward an inevitable collision. This approach took time millions of years. Tiny gravitational nudges gradually shifted Theia's path. Both worlds orbited the young Sun in slightly elliptical patterns. With each orbit, they inched closer. By the time Theia finally approached Earth, it was a fully formed planetary embryo, complete with its own molten interior. The collision that followed was one of the most energetic events in the history of the solar system. The impact occurred at an angle, not a direct head-on collision. This grazing strike released unimaginable energy, equivalent to billions of nuclear bombs detonating simultaneously. The force of the collision vaporized enormous amounts of rock and metal from both bodies. Much of Theia's mantle and a significant portion of Earth's outer layers were blasted into space. Molten droplets of silicate rock were hurled outward, forming a hot, glowing debris cloud encircling the planet. The impact reshaped Earth instantly. Its rotation sped up dramatically. A single day may have lasted as little as 4 to 6 hours after the collision. The spinning world bulged at the equator, distorted by the rapid rotation. The axis of rotation tilted significantly, creating the axial tilt that still governs Earth's seasons. Without this tilt, Earth's climate systems would be vastly different, lacking the complex seasonal patterns that help sustain diverse ecosystems today. Beneath the surface, the impact stirred Earth's interior. The collision caused the early core to grow hotter and denser. Material from Theia mixed with Earth, enriching the mantle with new elements. The heat unleashed by the impact created a global magma ocean, resetting the planet's crust. Any proto-continents that may have briefly formed in the Hadean were completely obliterated. The surface became a molten, fire-lit sea of rock. As the debris cloud cooled, particles began to clump together. Gravity pulled molten droplets into larger fragments. Within months or years, a short time on cosmic scales, these fragments merged into a single growing body. This body continued to attract surrounding debris, clearing a path around Earth's orbit. Eventually, it became the Moon. The Moon formed surprisingly close to Earth, likely only 20,000 to 30,000 kilometers away. At this distance, it appeared enormous in the sky, dozens of times larger than it appears today. Tidal forces between Earth and the infant Moon were intense. The Moon pulled on Earth's molten surface, creating tidal bulges of magma. These tides stirred the interior, helping to shape the early crust and mantle circulation. The gravitational interaction between Earth and the Moon slowed Earth's rotation over time, gradually elongating the length of a day. The Moon, meanwhile, drifted outward into a wider orbit. This slow outward migration continues even now. The Moon's creation also stabilized Earth's axial tilt. Without the Moon's gravitational anchor, Earth's tilt might have varied chaotically over millions of years, causing extreme climate shifts that could have hindered the development of stable environments. Instead, the Moon acts as a stabilizer, keeping the tilt within a relatively narrow range. This stability allowed Earth's climate to evolve over billions of years in a predictable pattern, enabling life to adapt and thrive. After the impact, Earth glowed with energy. Infrared radiation poured from its molten surface. The atmosphere thickened with vaporized rock, silicate droplets, and gases from the impact. The sky burned with red and orange hues, illuminated by the molten Earth and the glowing ring of debris that surrounded it. Over time, as the moon formed and the debris cleared, the atmosphere began to cool. Particles fell back to the surface as molten rain, further shaping the planet. The impact also contributed to Earth's chemical and isotopic composition. Studies of lunar rocks show remarkable similarities to Earth's mantle, confirming that the moon formed primarily from Earth's outer layers, not from Theia alone. This shared origin explains why the moon lacks a large iron core. Most of Theia's iron merged with Earth during the collision. The moon is therefore mostly silicate rock, a remnant of Earth's mantle cast into space. As the Earth-Moon system stabilized, new geological processes emerged. The immense heat from the impact slowly dissipated into space. A new crust began to form on the molten surface. Volcanic activity remained intense, releasing gases into the atmosphere. This outgassing helped form Earth's secondary atmosphere, dominated by carbon dioxide, nitrogen, and water vapor. In time, as the planet cooled further, water vapor would condense to create the first oceans. Theia's impact was not simply destructive, it was creative. It forged a double-world Earth and its moon forever linked in gravitational partnership. It established the planetary conditions necessary for long-term climate stability. It helped generate the core mantle dynamics that sustain Earth's magnetic field, a protector against solar radiation. It enriched the mantle with new materials, influencing the chemical evolution of the planet. The moon itself played a crucial role in the development of tides. Even when the oceans had not yet formed, its gravitational pull stirred the molten surface. Later, when liquid water covered Earth, tides would help mix nutrients, drive coastal ecosystems, and influence the biological rhythms of early life. The rhythmic ebb and flow of tides helped shape the environment in which life evolved. Without the moon, Earth's tides would be far weaker, and early coastal life may have developed differently. The impact also had long-lasting consequences for Earth's internal dynamics. The sudden injection of energy-enhanced mantle convection, promoting the early stages of plate tectonics. Earth's outer shell, though still forming, became more dynamic and mobile. This movement would eventually shape continents, build mountain ranges, and recycle nutrients through the crust. Plate tectonics is essential for maintaining a stable climate over billions of years because it regulates carbon dioxide through volcanic activity and rock weathering. Theia's collision indirectly set this engine into motion. As the moon slowly drifted outward, Earth continued to cool. The atmosphere cleared enough to expose the sky once more. Volcanic eruptions continued, releasing gases and shaping the landscape. But the violence of the Hadean era began to settle. The moon's presence created regular cycles, day and night, tides, rotational slowing that brought order to a once chaotic world. These cycles laid the foundation for the natural rhythms that would govern Earth throughout its history. The period after the Theia impact marked the transition from a molten world to a cooling planet capable of holding oceans and hosting chemical reactions that would one day lead to life. The impact set in motion a chain of events that guided Earth toward habitability. Without this collision, Earth might never have gained a large moon. And without a moon, Earth's climate stability, tides, and rotational balance would have been vastly different. Scientists believe that the Moon formed quickly within just a few thousand years after the impact. Once it reached its final form, it cooled into a solid, cratered world. Its surface preserves a record of early solar system bombardment, providing critical clues about the environment Earth experienced during its earliest eras. While Earth's active geology erased most evidence of the Hadean, the Moon retains this ancient history like a time capsule. With the Moon in place, Earth's evolution accelerated, its crust thickened, its interior layered more distinctly, the magnetic field strengthened, volcanic activity shaped the atmosphere. Water vapor began to accumulate and cool. Rain would soon fall for the first time, marking the beginning of the hydrological cycle that drives weather and erosion. But this moment came long after the impact's immediate aftermath. The Moon's creation also affected Earth's energy balance. It changed how sunlight reflected off the planet and how heat dissipated into space. It influenced the tilt of the axis, creating moderate seasonal changes. These changes prevented Earth from entering permanent climate extremes. Instead, the planet maintained oscillations that favored adaptability and evolutionary diversity. Over millions of years, the Earth-Moon system became one of the most stable partnerships in the solar system. While other planets experienced chaotic tilts, lost moons, or suffered major orbital instabilities, Earth and its Moon settled into a predictable pattern. This stability is one of the key reasons life could eventually emerge. In the aftermath of the Theia collision, Earth stood transformed. What had once been a molten, chaotic sphere was now a planet with structure, rhythm, and potential. The Moon orbited nearby, glowing white against the dark cosmic backdrop. The sky began clearing as debris settled. Volcanic plumes rose from the surface, painting streaks of red and orange across the horizon. Beneath the crust, the mantle churned with energy. The world was still violent, but its violence had purpose to shape the environment that would one day cradle life. Theia's impact marks the dividing line between Earth's raw formation and its progression toward habitability. It is the cosmic event that turned a molten sphere into a planet with oceans, continents, climate, and eventually, biology. Every living organism on Earth carries within it the legacy of this ancient collision. Every tide, every season, every eclipse is a reminder of the moment when two worlds became one. Earth and the Moon are forever bound by this shared origin. The impact was catastrophic, yet undeniably creative. From destruction came order, from chaos came structure. From molten debris came the beginnings of a stable, life-supporting world. And as Earth cooled, the next chapter prepared to unfold the formation of oceans, the thickening of crust, and the slow emergence of conditions that would make life possible. In the aftermath of the Theia collision, Earth remained a molten, glowing world. Its surface simmered at thousands of degrees, wrapped in an atmosphere thick with vaporized rock, carbon dioxide, sulfur compounds, and immense clouds of steam. The Moon, newly formed, circled close overhead, raising powerful tides in the molten surface below. Yet, even amid this hellish landscape, the foundations for oceans, continents, and stable crust were quietly taking shape. Earth was beginning the slow journey from fire to water, from chaos to equilibrium. As millions of years passed, heat radiated into space. The molten surface of Earth began to cool gradually. The magma ocean that had once engulfed the entire planet solidified from the outside in, forming a thin crust over the still molten interior. This crust was fragile and dynamic. Volcanic eruptions frequently shattered it, releasing new lava and gases into the atmosphere. Some regions cooled faster than others, creating thicker patches of crust precursors to the earliest continental fragments. Earth's early atmosphere played a central role during this cooling phase. After the first atmosphere was blasted away by solar winds and the Theia impact, volcanic outgassing built a second atmosphere composed primarily of carbon dioxide, water vapor, nitrogen, methane, and sulfur dioxide. This dense blanket trapped heat, slowing the planet's cooling. At the same time, it created a powerful greenhouse effect that kept the surface warm enough to prevent freezing while the interior continued to contract and cool. As the surface cooled, the temperature eventually dropped below the boiling point of water. This moment marked a dramatic transition. The vast amounts of water vapor trapped in the atmosphere, released from volcanoes, delivered by comets, and inherited from the planet's formation, began to condense. Clouds thickened. Storms intensified. For the first time in Earth's history, rain began to fall. The rain did not stop for millions of years. It poured relentlessly from the sky, filling basins, carving channels, and cooling the crust further. Each raindrop evaporated on contact with the still hot surface. But as cooling continued, more water remained liquid. Shallow pools formed in depressions. These pools grew into seas, and the seas expanded into primitive oceans. The hydrological cycle, evaporation, condensation, rainfall, began operating on a planetary scale. The formation of the oceans marked a turning point. Water is a powerful agent of change. It erodes rock, transports minerals, shapes landscapes, and regulates temperature. As the oceans grew, they absorbed carbon dioxide from the atmosphere, lowering greenhouse levels slightly and allowing further cooling. Oceans also acted as heat reservoirs, smoothing temperature fluctuations and stabilizing the young planet's climate. Beneath the surface, the mantle continued to churn. Convection currents pushed molten rock upward, creating volcanoes and igneous intrusions. These volcanic regions produced new crust, while older crust sank or fractured under the weight of accumulating water. The earliest form of plate tectonics may have begun during this time. The crust was thinner, hotter, and more flexible than today's, but water weakened it, allowing it to break into segments. These segments moved slowly, driven by the mantle's heat. This movement created new geological features, ridges, trenches, and volcanic arcs. The earliest continental fragments, known as cratons, began forming from buoyant, silica-rich rocks created deep within the mantle. These rocks were lighter than the surrounding basaltic crust, allowing them to float higher, resisting submersion beneath the oceans. Over time, these primitive continents grew through repeated melting and solidification. Volcanic activity added new material. Impacts from meteorites delivered additional minerals. The crust thickened, creating stable regions that would eventually become the cores of modern continents. The oceans themselves were far different from the blue waters of today. Early oceans were likely greenish or brownish, filled with dissolved iron and minerals leached from the crust. The atmosphere lacked oxygen, so iron remained in its soluble form, giving the water a distinct chemical character. Hydrothermal vents dotted the seafloor, releasing hot, mineral-rich fluids that reacted with seawater. These vents created complex chemical environments that scientists believe may have played a role in the origin of life. As Earth cooled further, the atmosphere continued to evolve. Volcanic eruptions released ongoing supplies of gases. Carbon dioxide remained abundant, maintaining a greenhouse effect strong enough to counter the faint young sun, which shone at only about 70% of its current brightness. Without this greenhouse effect, Earth might have frozen into a global ice world before life had a chance to emerge. Instead, the balance between volcanic emissions and oceanic absorption kept the climate warm enough for liquid water. The Moon played a crucial role during this era. Though it had moved farther from Earth than during its formation, it still orbited close enough to exert enormous tidal forces. These tides stirred the early oceans. Enhancing chemical mixing, the tidal cycles helped distribute heat and nutrients, shaping the conditions in which early chemical reactions occurred. The rhythmic rise and fall of the tides added structure to a world still finding its equilibrium. The crust continued to thicken. Volcanic island chains erupted throughout the oceans, forming archipelagos. These islands eroded under constant rainfall, delivering sediments into the seas. Sedimentary layers accumulated on the ocean floor, marking the first geological records preserved on Earth. While most Hadean rocks have been destroyed by tectonic recycling, tiny zircon crystals, some over 4 billion years old, remain as evidence of early crust and liquid water. These zircons tell a remarkable story. They contain oxygen isotopes that indicate interactions with liquid water at surprisingly early times. This means oceans may have existed while the surface was still cooling from the Theia impact. Earth transitioned to a water world far sooner than once believed. The presence of water helped moderate temperatures and accelerate geological processes. Even in its youth, Earth was already exhibiting features of a dynamic, evolving planet. As oceans expanded, they began covering most of the planet's surface. Earth may have appeared almost entirely blue, dotted only by small volcanic islands and tiny continental fragments. The deep ocean basins formed as the crust thinned in some areas. Mid-ocean ridges released magma that cooled rapidly, creating dense basalt. This basalt sank, forming deeper regions that filled with water. The interplay between ridges and basins shaped the global ocean system. The atmosphere gradually cleared of dust and debris. Thick clouds dominated the sky, but sunlight increasingly reached the surface. Volcanic gases continued influencing climate. Sulfur dioxide reacted with water to form acid rain, which etched rocks and altered the chemistry of the oceans. Carbon dioxide dissolved in seawater, forming carbonic acid and regulating atmospheric composition. Nitrogen accumulated as a stable atmospheric gas, forming the foundation of Earth's modern atmosphere. While oxygen remained absent, other gases played active roles. Methane, produced by geological processes, contributed to warming. Ammonia influenced early chemical reactions. Lightning storms continued to energize the atmosphere, breaking molecules apart and creating new ones. Ultraviolet radiation from the sun penetrated the atmosphere, interacting with water and volcanic gases to form complex organic molecules. Though life had not yet emerged, the planet was becoming increasingly chemically rich. Earth's crust, though more stable than during the Hadean, still experienced frequent impacts. The late heavy bombardment, a period of intensified asteroid strikes, occurred near the end of this era. Massive impacts vaporized portions of oceans, melted crust, and temporarily sterilized large regions of the planet. Despite this destruction, life would later emerge, showing the resilience of Earth's systems. But before life could rise, the planet needed to reach a new level of stability. As cooling continued, the mantle's convection patterns evolved. Heat escaped more efficiently through the thicker crust, allowing deeper mantle layers to solidify slightly. This change increased the contrast between oceanic and continental crust. Continental crust, being lighter and thicker, remained above sea level more consistently. Oceanic crust, thinner and denser, formed vast basins. This differentiation laid the foundation for the future arrangement of continents and oceans. The oceans themselves became more complex. Temperature gradients formed between shallow coastal regions and deep ocean trenches. Hydrothermal vent systems created chemically rich environments on the sea floor. These vents expelled superheated water laden with minerals, creating towering chimneys of solidified minerals known as black smokers. The boundary between hot vent water and cold ocean water produced steep chemical gradients ideal for early chemical evolution. The atmosphere stabilized enough to create the first weather patterns. Winds circulated heat from the equator to the poles. Storms formed as warm ocean water evaporated and condensed into clouds. Rainfall shaped the landscape, breaking down rocks and transporting minerals. Erosion sculpted early land masses. Sediment deposition created layered rocks, some of which survive today as the world's oldest geological formations. The cooling of the crust also strengthened Earth's magnetic field. As the core continued to differentiate, the dynamo effect in the liquid outer core intensified. This magnetic shield protected the atmosphere from being stripped away by solar winds. The preservation of the atmosphere was crucial for the stability of the oceans. Without the magnetic field, Earth might have lost its water to space, as happened on Mars. Over time, the oceans reached near modern volumes. Water covered most of the planet, creating a global environment capable of supporting complex chemistry. The oceans acted as a vast solvent, dissolving minerals and mixing elements. These elements would later become essential components of life. Among them were carbon, nitrogen, phosphorus, sulfur, and various trace metals. The oceans became a planetary laboratory, conducting endless chemical experiments. The presence of stable oceans also allowed Earth to reflect sunlight more effectively. The planet cooled further, balancing greenhouse effects and solar radiation. Climate cycles began to emerge. The rotation of the Earth slowed slightly as tidal friction from the Moon continued to influence motion. Each change contributed to the development of a stable environment. The earliest forms of continental crust grew larger. Volcanic islands merged, forming larger land masses. These continents remained small compared to today's, but they provided diversity in habitats, rocky shores, shallow seas, volcanic plains, and deep basins. These varied environments played crucial roles in shaping the future of life. Life would not emerge uniformly. It would arise in specific environments where chemical gradients and stability aligned. By the end of this era, Earth had transformed from a molten inferno into a water-rich world with a thickening crust. Its atmosphere, though still hostile to modern life, supported a stable climate. The oceans circulated heat, mixed nutrients, and provided a medium for chemical evolution. The continents began to form the skeleton of future geology. The Moon hung in the sky, gradually drifting outward, but still dominating tidal patterns. Earth was now ready for the next chapter, the emergence of life. But before life could appear, the planet needed further chemical evolution, driven by the oceans, the atmosphere, and the energy from the sun and mantle. The stage was set. A once fiery planet had cooled enough to host liquid water, stable crust, and complex chemistry. From fire came water. From chaos came stability. And within this stability, the first whispers of life were beginning to take shape. The Earth, now cooled enough to hold vast oceans, entered a new and remarkable chapter. The violent bombardment of the Hadean had subsided. The molten crust had hardened into a more stable surface. Clouds parted enough for sunlight to reach the oceans. Volcanic islands rose from steaming waters. Hydrothermal vents pierced the seafloor, releasing plumes of mineral-rich fluids into the dark abyss. Everywhere, chemistry was unfolding on a planetary scale. In this world, there were no plants, no animals, not even microbes. Yet the ingredients for life collected in the oceans, waiting for the moment when matter would cross the boundary into biology. Earth's early oceans were far from calm or simple. They were dynamic, filled with dissolved minerals, metals, and gases absorbed from volcanic eruptions and hydrothermal vents. Ultraviolet radiation from the young sun penetrated the upper layers of water, breaking molecules apart and producing new ones. Lightning storms energized the atmosphere, creating reactive compounds that washed into the seas. Meteorites delivered organic molecules formed in the interstellar medium. The oceans became a vast chemical laboratory full of potential. Life did not begin with a single spark or a single event. Instead, it emerged through countless interactions among molecules, driven by energy from the sun, the Earth's interior, and the environment itself. These interactions produced increasingly complex combinations of carbon-based molecules, amino acids, nucleotides, lipids, and sugars formed through a mix of geological and atmospheric processes. These molecules concentrated in specific environments: tidal pools, hydrothermal vents, volcanic lakes, and mineral-rich sediments. One of the most compelling environments for the origin of life existed deep beneath the ocean's surface: hydrothermal vents. Here, hot water rich in hydrogen, methane, and mineral ions flowed through cracks in the crust. When this superheated water met cold seawater, it created steep chemical gradients. These gradients provided energy that could drive chemical reactions. Mineral structures at these vents, particularly porous iron-sulfur formations, acted like natural reactors. Their tiny compartments offered protection, concentration, and catalytic surfaces for early molecules to assemble into more complex forms. In these environments, simple organic molecules began forming chains. Peptides formed from linked amino acids. Nucleotides bonded to create short strands resembling primitive RNA. Lipids assembled into spherical membranes that trapped molecules inside. These early membranes were fragile, but they represented a crucial step. They created boundaries. Life requires separation, an inside and an outside, and these lipid bubbles offered the first primitive form of cellular structure. The next challenge was replication. For life to take hold, molecules needed the ability to copy themselves. Before DNA existed, scientists believe RNA-like molecules played this role. RNA is capable of both storing information and catalyzing chemical reactions in the primordial seas. Short RNA strands may have formed spontaneously, aided by mineral surfaces that stabilized their structure. Some of these strands could fold into shapes that allowed them to copy parts of themselves. Imperfect copying introduced variation. Variation introduced evolution. Over time, the most stable and efficient sequences persisted. These replicating molecules did not exist alone. They interacted with lipids, peptides, minerals, and environmental forces. Eventually, some replicators became enclosed within lipid membranes. This created the first protocells, simple vesicles containing genetic material and chemical machinery. Though incredibly primitive, these protocells had two essential properties. They maintained internal chemistry and they reproduced, even if crudely. From this point forward, evolution had something to work with. The oceans provided the perfect environment for protocells to survive. Currents carried nutrients. Tides created cycles of concentration and dilution. Ultraviolet light induced mutations, creating new molecular variations. Hydrothermal vent systems offered stable energy gradients, while shallow pools offered cycles of drying and refilling that concentrated molecules to useful levels. Protocells that survived environmental pressures grew more complex over time. The first true cells likely emerged when protocells stabilized their internal chemistry enough to sustain metabolism. Metabolism refers to the ability to use energy from the environment to drive chemical reactions inside the cell. Early metabolism may have been simple, relying on chemical gradients near vents. Over time, cells developed more sophisticated ways to generate energy. They used minerals like iron and sulfur to fuel reactions. They developed membranes that controlled the flow of ions, creating internal environments different from the outside world. These first cells were prokaryotes, simple, single-celled organisms with no nucleus. They were unlike anything alive today, yet they shared fundamental traits with modern bacteria and archaea. They possessed genetic material, membranes, metabolic pathways, and the ability to reproduce. Though microscopic, they represented a monumental step in the history of the planet. Inanimate matter had transitioned into living organisms. Once life began, it spread through the oceans. Early cells colonized hydrothermal vent systems, clinging to mineral surfaces. Others drifted in ocean currents, carried to new environments. Some adapted to shallow waters, where sunlight was available. Others survived near volcanic islands, feeding on chemical gradients produced by eruptions. Although life remained single-celled for a long time, it was already transforming the planet. One of the most profound transformations came with the evolution of photosynthesis. Before photosynthesis, early cells relied on chemical energy from the environment. This limited their growth and distribution. But some cells developed pigments capable of capturing sunlight. These pigments allowed them to harness light energy to drive chemical reactions. The earliest photosynthetic organisms may not have produced oxygen. They likely used hydrogen sulfide or other molecules instead. But eventually, a revolutionary pathway evolved: oxygenic photosynthesis. Oxygenic photosynthesis uses water as an electron source, releasing oxygen as a byproduct. When this process emerged, it changed the entire future of Earth. Suddenly, life could tap into an almost unlimited energy source, sunlight, and use water, one of the most abundant molecules on Earth, as fuel. This dramatically increased productivity in the oceans, setting the stage for further biological innovation. But oxygen was toxic to many early organisms. When oxygen first accumulated in localized environments, it caused oxidative stress. Some organisms died, others adapted. Still others sought refuge in oxygen-free regions. Over millions of years, oxygen levels began rising gradually in the oceans and atmosphere. This rise would culminate in the Great Oxygenation event, a turning point that reshaped the planet. But that transformation belonged to a later era. In the early stages, life continued evolving in low oxygen conditions. Prokaryotes diversified into numerous metabolic forms. Some used sulfur, others used iron. Some fed on methane, others produced methane. The methane in the atmosphere contributed to a warming effect that helped compensate for the faint young sun. Biology and climate became intertwined, each influencing the other. The oceans themselves transformed as life expanded. Microbial mats formed on shallow sea floors, trapping sediments and creating layered structures known as stromatolites. These stromatolites are among the oldest fossils on Earth, dating back more than 3.5 billion years. They provide evidence that early microbial life was already forming complex communities. Within these mats, different microorganisms lived in layers, each performing specialized functions. Some absorbed sunlight, others broke down chemical wastes. Together, they created miniature ecosystems. The chemical composition of the oceans continued to shift. Dissolved iron reacted with oxygen produced by early photosynthetic organisms, forming iron oxide minerals that sank to the seafloor. These deposits created banded iron formations, geological layers that record the growing influence of biology on the planet. Each layer reveals a moment in Earth's chemical history, connecting geology and biology in a shared timeline. Life also influenced the stability of the crust. Microbial activity contributed to weathering, breaking down minerals, and altering the surface chemistry of rocks. Sediments created by biological processes built layers on the ocean floor, affecting tectonic movements. Although life remained microscopic, its impact grew steadily. The early atmosphere, while still harsh by modern standards, became more stable. Nitrogen dominated. Carbon dioxide remained abundant, but gradually declined as oceans and early organisms absorbed it. Methane from microbes contributed to warming. The interplay between gases created a delicate balance that kept Earth's temperature within a range suitable for liquid water. Evolution continued. Natural selection favored cells with more efficient membranes, more accurate replication, and more robust metabolic pathways. Diversity increased. Some cells specialized in certain environments, others adapted to extreme conditions, living near boiling vents or highly acidic waters. These extremophiles demonstrated that life could thrive in a wide range of habitats. They also revealed the resilience of early life, capable of surviving conditions far more extreme than most modern organisms. As time passed, genetic innovation gave rise to more complex biochemical systems. Enzymes became more specialized. Metabolic pathways became more interconnected. Cells gained the ability to repair damage, regulate internal chemistry, and adapt to environmental changes. Although the first billion years of life remained purely microbial, this period established the foundation for all future biological evolution. The oceans, once purely chemical environments, had become biological seas filled with microscopic life. These organisms interacted with geology, chemistry, and climate, influencing the entire planet. The emergence of life marked the beginning of a new era in Earth's story, one in which biology and geology would continually shape each other. Earth's journey from stardust to a living world was extraordinary. The birth of life in the primordial seas was not guaranteed. It required the right conditions, the right chemistry, and the right sequence of events. But once life emerged, it became an unstoppable force of transformation. From simple molecules came replicators. From replicators came protocells. From protocells came the first true organisms. These organisms would eventually give rise to the entire tree of life, from bacteria to animals to humans. And as life flourished, the next great transformation approached, the rise of prokaryotes and the long evolutionary journey toward complexity. After life first emerged in Earth's primordial oceans, the planet entered a new chapter, dominated entirely by microscopic organisms. These earliest inhabitants, prokaryotes, reshaped the chemistry of the atmosphere, altered the composition of the oceans, and laid the biological groundwork for every form of life that would follow. For more than 1 billion years, prokaryotes ruled the planet. Though invisible to the naked eye, their influence was immense. They were architects of ecosystems, engineers of chemical cycles, and the silent force guiding Earth toward complexity. Prokaryotes are simple cells with no nucleus. Their genetic material floats freely within the cytoplasm. Their membranes are thin but functional. Their metabolisms are versatile and inventive. These traits allowed them to survive in environments that would kill most modern organisms. When prokaryotes first appeared, Earth was a harsh world with volcanic activity, frequent impacts, high ultraviolet radiation, and oceans filled with dissolved metals. Yet prokaryotes adapted with remarkable ease, spreading from shallow coastal waters to deep ocean vents. At hydrothermal vents, early archaea, one of the two main branches of prokaryotes, found energy in chemical gradients created by the mixing of hot vent water and cold ocean water. These organisms used hydrogen, sulfur, and methane in their metabolic pathways. They fed on inorganic molecules, relying on the planet's internal heat rather than sunlight. This type of metabolism, known as chemosynthesis, allowed life to thrive in complete darkness. Even today, deep-sea vent communities rely on similar chemical processes, reminders of ancient ecosystems that once dominated Earth. Other prokaryotes settled in shallow waters where sunlight penetrated. They developed pigments capable of capturing light and converting it into chemical energy. This innovation marked the beginning of photosynthesis. At first, photosynthetic organisms used hydrogen sulfide rather than water as an electron donor, producing sulfur instead of oxygen. These early photosynthesizers were crucial because they expanded the availability of energy. Sunlight, abundant and constant, became a source of fuel for life. Eventually, a revolutionary adaptation appeared: oxygenic photosynthesis. This process used water as a source of electrons, releasing oxygen as a byproduct. Cyanobacteria, the prokaryotes responsible for this development, transformed the chemistry of the oceans and atmosphere. Oxygen was initially toxic to many early organisms, but cyanobacteria thrived because it allowed them to access an unlimited supply of water. Using sunlight and water, they produced energy with extraordinary efficiency. Cyanobacteria formed sprawling microbial mats in shallow seas. These mats trapped sediments and built layered structures known as stromatolites. These formations still exist today in a few isolated locations. But 3 billion years ago, they dominated the coastlines. Stromatolites served as living factories, continuously producing oxygen and altering the planet's atmosphere, layer by layer. They grew upward, preserving evidence of early life within their mineral skeletons. As cyanobacteria continued releasing oxygen, the oceans began to change. Dissolved iron in seawater reacted with the oxygen, forming solid iron oxides that settled on the ocean floor. This process created the famous banded iron formations, layered rocks that reveal shifting oxygen levels over geological time. Each band of iron represents a chapter in the story of Earth's transformation, written not by rivers or volcanoes, but by microscopic life. For a long time, oxygen produced by cyanobacteria was absorbed by the oceans and seafloor minerals. The atmosphere remained largely anoxic. Prokaryotes diversified in this low oxygen world, adapting to an array of ecological niches. Some became methanogens, producing methane, a powerful greenhouse gas that helped warm the planet under a faint young sun. Others became sulfate reducers, breaking down sulfur compounds. Still others specialized in nitrogen fixation, transforming nitrogen gas into biologically usable forms. This nitrogen fixation would become essential for all future life, as nitrogen is a fundamental component of DNA, proteins, and cell structures. As prokaryotes diversified, they formed complex ecosystems long before plants or animals existed. Microbial colonies covered vast areas of seafloor in shallow waters. Cyanobacteria built stromatolite forests. In deep ocean vents, archaea fed on hydrogen sulfide, supporting entire communities of organisms. Even beneath the sea floor, microbes lived within rock pores, feeding on the chemical energy released by interactions between water and minerals. Earth was alive at every depth. Prokaryotes also developed remarkable resilience. They evolved the ability to form spores, allowing them to survive extreme heat, cold, drought, and radiation. Some found refuge deep underground. Others survived freezing temperatures near the poles. This adaptability ensured that prokaryotes remained the most abundant and diverse form of life on the planet. Over time, oxygen produced by cyanobacteria began to accumulate in the oceans faster than it could react with minerals. Once the supply of easily oxidized materials was exhausted, oxygen levels rose more rapidly. Eventually, oxygen escaped into the atmosphere. This began a slow but profound transformation known as atmospheric oxygenation. Oxygen levels rose from near zero to detectable levels for the first time in Earth's history. Oxygen changed everything. For anaerobic organisms, oxygen was toxic. It damaged cellular structures and disrupted metabolic pathways. Many early prokaryotes went extinct. Others retreated into environments where oxygen could not reach, such as deep sediments, vents, and oxygen-poor waters. A few organisms evolved defenses against oxygen, developing enzymes capable of neutralizing reactive oxygen molecules. These adaptations allowed aerobic respiration to evolve. Aerobic respiration was far more efficient than anaerobic metabolism. Oxygen acted as a powerful electron acceptor, allowing organisms to extract significantly more energy from food molecules. This gave aerobic prokaryotes a tremendous advantage. They multiplied rapidly, colonizing new environments and diversifying into countless lineages. The rise of oxygen did not merely change the atmosphere, it changed the trajectory of life itself. As oxygen accumulated in the atmosphere, it also reacted with methane, reducing the greenhouse effect. This shift in atmospheric composition contributed to global cooling. Scientists believe these changes may have triggered one of Earth's earliest ice ages, possibly even a global glaciation. Prokaryotes survived this cold world, adapting to frozen oceans and icy conditions. Microbial life persisted beneath ice sheets, near hydrothermal vents, and in pockets of unfrozen water. During these transformations, prokaryotes continued to innovate genetically. Horizontal gene transfer, the ability to share genes between unrelated organisms, accelerated evolution. Unlike animals and plants, prokaryotes could exchange segments of DNA directly. This allowed beneficial mutations, such as antibiotic resistance or new metabolic pathways, to spread rapidly. Gene sharing turned microbial evolution into a collective process, enabling populations to adapt to new conditions with extraordinary speed. One of the most important evolutionary innovations occurred when some prokaryotes developed internal membrane folds, increasing the surface area for metabolic reactions. These folds may have been precursors to the internal structures found in later eukaryotic cells. Some prokaryotes also evolved primitive cytoskeletons, flexible protein frameworks that allowed them to change shape and move more effectively. Although still simple compared to modern cells, these adaptations hinted at the complexity to come. Prokaryotes did more than survive, they shaped the planet. They controlled the carbon cycle, breaking down organic matter and releasing nutrients back into the environment. They influenced the sulfur cycle, creating chemical gradients in ocean sediments. They fixed nitrogen, enabling future ecosystems to exist. Their metabolic activities helped regulate climate, atmospheric composition, and ocean chemistry. For billions of years, Earth was a microbial world, engineered and maintained by prokaryotes. Their power extended even deeper. Prokaryotes in the subsurface, living kilometers beneath the seafloor, created long-lasting ecosystems independent of sunlight. These deep biosphere organisms fed on hydrogen produced by water interacting with minerals in the crust. They reproduced slowly, sometimes dividing only once every 1,000 years. Yet they persisted, forming one of the largest reservoirs of life on the planet. Even today, the deep biosphere contains more biomass than all plants and animals combined. By this time, Earth's oceans and atmosphere were no longer purely geological constructs. They were biological systems shaped by living organisms. Oxygen levels continued to rise, eventually leading to the Great Oxygenation event, a turning point that belongs to the next chapter. But before the Great Oxygenation, prokaryotes achieved one of the most astonishing innovations in the history of life: the symbiotic merging of different prokaryotic cells. Some archaea engulfed bacteria, but did not digest them. Instead, the bacteria survived inside their hosts, providing energy in exchange for protection. This partnership marks the beginning of the eukaryotic cell, mitochondria, the energy-producing organelles in all complex life, originated from these engulfed bacteria. Later, some eukaryotes engulfed cyanobacteria, giving rise to chloroplasts, the structures that perform photosynthesis in plants. This moment, when one cell lived inside another, was one of the most important leaps in evolution. It created the foundation for complex life. Yet this transformation was possible only because prokaryotes had spent billions of years diversifying, adapting, and altering the planet's chemistry. Prokaryotes ruled Earth for most of its history. They created the atmosphere we breathe. They set the stage for the evolution of plants, animals, and humans. They built the world molecule by molecule. Without prokaryotes, Earth would remain barren and lifeless. Their legacy is still with us. In every human body, trillions of bacteria help digest food, regulate immunity, and maintain health. In every ecosystem, prokaryotes recycle nutrients and support food webs. In every ocean, they produce oxygen and drive chemical cycles. Even after billions of years, the planet remains a microbial world at its core. By the end of this era, Earth had undergone profound change. Oxygen levels began to rise significantly. Microbial ecosystems had matured. The first eukaryotic cells were beginning to form. The world was ready for the next dramatic transformation, the Great Oxygenation event, a shift that would alter the climate, reshape the surface, and pave the way for complex life. For billions of years, Earth had been a world ruled by prokaryotes, thriving in oxygen-free oceans and atmospheres. Life was purely microbial, adapted to a chemistry dominated by methane, carbon dioxide, nitrogen, sulfur, and dissolved metals. The oceans were greenish and iron-rich. The skies were hazy, tinted by volcanic gases. Sunlight filtered through an atmosphere without ozone. And across the shallow seas, cyanobacteria continued to perform oxygenic photosynthesis, a groundbreaking innovation that would eventually trigger one of the most dramatic transformations in the planet's history. This transformation is known as the Great Oxygenation event, and it would change the face of Earth forever. For millions of years after cyanobacteria evolved oxygenic photosynthesis, the oxygen they produced did not accumulate in the atmosphere. It was immediately consumed by chemical reactions in the oceans. Vast quantities of dissolved iron absorbed the oxygen, forming solid iron oxides that drifted to the seafloor. These deposits became banded iron formations, alternating layers of iron-rich minerals that still serve as geological witnesses to this ancient era. Each layer marks a moment when oxygen levels surged, triggering precipitation of iron before atmospheric accumulation could begin. For a long time, this process acted as a chemical buffer, preventing oxygen from entering the atmosphere in significant amounts. But the supply of dissolved iron was finite. Eventually, the oceans became saturated. Once the iron was fully oxidized, it could no longer absorb oxygen. At this tipping point, cyanobacteria continued releasing oxygen, but the oceans no longer had the capacity to neutralize it. Slowly, oxygen began to accumulate. At first, the rise was modest, tiny increases in atmospheric concentration barely detectable. But over time, the oxygen curve steepened. Earth's atmosphere entered a new phase. Rising oxygen levels created massive consequences. For many early organisms, oxygen was poisonous. Anaerobic microbes, which had evolved in a world without oxygen, suffered as reactive oxygen molecules damaged their proteins, membranes, and DNA.
These organisms were forced into oxygen, poor refuges, deep sediments, hydrothermal vents, and isolated environments where oxygen could not penetrate. Vast numbers of anaerobic species likely went extinct.
It was one of Earth's earliest mass extinctions, invisible to the naked eye but enormous in impact. As oxygen increased, it also reacted with methane in the atmosphere. Methane had been one of the most significant greenhouse gases, helping keep Earth warm under a faint young sun. Oxygen stripped methane from the atmosphere, converting it into carbon dioxide and water. This reduction in methane weakened the greenhouse effect, allowing Earth to lose more heat to space. Global temperatures dropped significantly. Some studies suggest this cooling triggered one of the first major glaciations in Earth's history, possibly even a Snowball Earth, where ice covered large portions of the planet. Although debate continues about the extent of this glaciation, it is clear that the Great Oxygenation event had the power to reshape global climate. Oxygen's rise also transformed the chemistry of the atmosphere and oceans. Oxygen reacted with gases like hydrogen sulfide, reducing their abundance. It oxidized minerals on land, creating soils and binding metals into new forms. For the first time, oxidative weathering became a major geological process. This weathering released nutrients into rivers and oceans, altering marine ecosystems and opening opportunities for new microscopic life. As oxygen accumulated, the upper atmosphere began forming ozone, a molecule composed of 3 oxygen atoms. Ozone plays a crucial role in blocking harmful ultraviolet radiation from the sun. Before the ozone layer existed, Earth's surface was bombarded by intense UV light, limiting life to underwater environments or shaded regions. The formation of the ozone layer reduced UV exposure, allowing future life forms to explore shallower waters and eventually reach land. This protection marked a turning point, enabling biological expansion that would unfold over billions of years. While oxygen was dangerous to some life forms, it offered tremendous advantages to others. Aerobic respiration evolved as a powerful metabolic pathway. Organisms that could use oxygen to break down organic molecules extracted far more energy than anaerobic organisms could. This energy surplus supported more complex cellular structures and faster growth. aerobic prokaryotes flourished, diversifying rapidly in the oxygenated environment. The stage was set for one of the most important evolutionary leaps in history, the development of eukaryotic cells. Though eukaryotes did not immediately dominate during the Great Oxygenation event, the rising oxygen levels created the conditions necessary for their emergence. Mitochondria, the energy-producing organelles within eukaryotic cells, evolved from aerobic bacteria that entered into symbiotic relationships with other prokaryotes. This symbiosis was only possible because oxygen had become a stable part of the environment. Thus, the Great Oxygenation event indirectly laid the foundation for all complex life: plants, fungi, animals, and eventually humans. As oxygen transformed the planet's chemistry, the appearance of rust-colored soils became widespread. Iron minerals oxidized, staining landscapes red. These red beds are geological markers of the rise of oxygen. They reveal a world undergoing dramatic oxidation, with new minerals forming on continents and in ocean basins. The chemistry of rocks forever changed, reflecting the arrival of free oxygen in the atmosphere. The oceans also evolved. Once filled with dissolved iron, they gradually became clearer as the iron precipitated out. Oxygen began diffusing into surface waters, creating stratified layers. The upper ocean became oxygen-rich, while deeper layers remained anoxic for much longer. This stratification influenced marine life, driving new forms of metabolism and ecological partitioning. Some microbes specialized in oxygen-rich zones. Others survived in the oxygen-poor depths, maintaining ancient metabolic pathways that predated atmospheric oxygen. The Great Oxygenation event unfolded over hundreds of millions of years. It was not a sudden shift, but a complex, multi-stage transformation. Oxygen levels rose in pulses, influenced by climate, volcanic activity, tectonic movements, and biological evolution. Sometimes, oxygen increased rapidly, triggering bursts of oxidation. Other times it stabilized or even declined. But the long-term trend was unmistakable. Earth was transitioning into an oxygenated world. This transition dramatically altered Earth's energy cycles. With oxygen abundant, new chemical reactions became possible. Combustion could occur. Organic matter could burn. Oxidative decay became a central part of the carbon cycle. Ecosystems, even though still microbial, gained access to new resources and new modes of survival. As oxygen levels continued rising, atmospheric pressure and composition changed enough to influence weather patterns. Storms evolved. Rainfall chemistry shifted. Lightning frequency may have changed. Each alteration influenced chemical cycles on land and in the oceans. Even without plants or animals, the environment was becoming increasingly complex. During this time, prokaryotes continued to drive most biological processes. Cyanobacteria thrived in sunlit waters, forming large colonies and mat structures. These mats covered coastlines, creating oxygen-rich microenvironments. Beneath them, anaerobic organisms found refuge. These layered microbial ecosystems were precursors to future biodiversity. Even in their simplicity, they demonstrated patterns of cooperation, competition, and specialization. As oxygen accumulated further, it began penetrating deeper into the oceans. Sulfate concentrations rose as sulfur reacted with oxygen, altering marine chemistry. Increased sulfate supported the evolution of sulfate, reducing bacteria, which played major roles in nutrient cycling. Nitrogen cycling also intensified, with nitrifying and denitrifying bacteria becoming more active. These changes were essential for maintaining global nutrient balance. The Great Oxygenation event also affected tectonic and geological processes. Oxidation of the crust weakened certain minerals and altered rock composition, influencing erosion rates and sediment formation. Increased weathering delivered more nutrients to the oceans, potentially boosting biological productivity. As productivity increased, more organic matter accumulated on the seafloor, altering carbon burial rates. Carbon burial, in turn, influenced atmospheric composition. Earth had entered a tightly coupled system where geology, chemistry, and life continually shaped one another. For anaerobic organisms, the Great Oxygenation was a biological catastrophe. Countless species vanished, pushed into extinction by the rise of a toxic gas they could not tolerate. But this extinction opened ecological space for aerobic organisms, which flourished in the new oxygen-rich environment. These aerobic microbes became the ancestors of the mitochondria that now power every eukaryotic cell. Their success marked a turning point in life's trajectory. Over time, oxygen levels reached a plateau, stabilizing at concentrations still far lower than today's. Earth had become a partially oxygenated world, with significant differences between atmospheric layers and ocean depths. This new environment supported increasing biological complexity, paving the way for the emergence of eukaryotic cells, the next major evolutionary step. The Great Oxygenation event is one of the planet's most important transformations. It reshaped the atmosphere, changed the climate, altered the oceans, created new ecological niches, and laid the foundation for complex life. It marked the end of the purely microbial world and the beginning of a planet capable of supporting larger, more energy-demanding organisms. Without this event, Earth would remain an anaerobic world, devoid of plants, animals, and humans. The oxygen we breathe today is a legacy of cyanobacteria that lived billions of years ago, tirelessly producing oxygen long before any creature with lungs existed. By the end of the Great Oxygenation event, Earth had become a different planet. The skies were clearer. The oceans separated into oxygen-rich and oxygen-poor layers. The land bore the scars of oxidation. And deep within the microbial world, new possibilities were emerging, possibilities that would eventually lead to the evolution of eukaryotes, multicellular organisms, and the vast diversity of life that would come to populate Earth. The planet had taken its first breath of oxygen. The next chapter would reveal the consequences of this profound shift, including global ice ages, new ecosystems, and the rise of increasingly complex life. After the Great Oxygenation event reshaped Earth's atmosphere and oceans, the planet entered one of the most extreme climatic chapters in its history. Oxygen levels had risen enough to disrupt the balance of greenhouse gases, particularly methane, which until then had kept the young Earth warm under a faint sun. With methane levels falling and carbon dioxide unable to fully compensate, temperatures began to drop, slowly at first, then rapidly. The world drifted toward a global chill that would culminate in what scientists call Snowball Earth, a time when ice may have stretched from the poles to the equator, turning Earth into a frozen sphere. This transformation did not occur all at once. Climate fluctuations were influenced by volcanic activity, continental positions, orbital changes, and biological feedback loops. But the weakening greenhouse effect played the central role. Methane, a powerful heat-trapping gas, reacted with rising oxygen to form carbon dioxide and water. Although carbon dioxide is also a greenhouse gas, it was not abundant enough to replace the warming power of methane. The atmosphere cooled. Oceans began absorbing more heat than they retained. Glaciers formed at the poles and slowly crept toward lower latitudes. The continents of the time were arranged differently from today. Most land masses were clustered near the equator, which meant that once ice began forming on tropical continents, it reflected enormous amounts of sunlight back into space. This reflectivity, or albedo, triggered a runaway effect. The more ice that formed, the more sunlight was reflected away. The more sunlight was reflected, the colder Earth became. This feedback loop accelerated cooling, pulling the planet deeper into a global freeze. As temperatures continued to fall, oceans began to freeze along their surfaces. At first, the ice sheets were thin and patchy, melting during warm seasons and refreezing during colder periods. But once ice reached lower latitudes, the process accelerated. Water beneath the ice remained liquid, warmed slightly by geothermal heat, but the surface froze into a thick shell. Eventually, ice may have covered the entire ocean, forming layers up to a kilometer thick. The continents, too, lay buried under immense glaciers. Mountain tops disappeared under white blankets of frozen snow and compacted ice. Earth became a world wrapped in ice. The atmosphere thinned as water vapor. A greenhouse gas condensed and froze out of the air. Storms diminished. Rainfall ceased. Evaporation nearly vanished. The hydrological cycle slowed to a near halt. Dust storms swept across the icy surface, driven by katabatic winds descending from towering ice sheets. The oceans, insulated beneath the ice, became isolated worlds of their own. Life persisted, but barely. Ecosystems that had flourished in shallow sunlit waters were devastated. Cyanobacteria, once dominant in surface waters, retreated into cracks and melt pockets where light still penetrated thin ice. Some survived near volcanic hotspots, where geothermal heat created small regions of open water known as polynyas. Other microbes sought refuge around hydrothermal vents, far below the frozen surface. These vents released hot, mineral-rich water that sustained entire communities independent of sunlight. The deep ocean biosphere, already thriving on chemical energy, became a crucial reservoir of life. Chemical cycles also slowed dramatically. The weathering of rocks, a major sink for carbon dioxide, nearly stopped because ice covered most land masses. With weathering reduced, volcanic carbon dioxide gradually accumulated in the atmosphere. But the buildup was extremely slow, requiring millions of years to reach levels capable of warming the planet again. Beneath the ice, the oceans remained dynamic. Currents circulated heat and nutrients. Hydrothermal vents produced chemical gradients that fueled microbial ecosystems. Sediments continued to accumulate on the seafloor. Some organisms developed new metabolic pathways to exploit chemical energy more efficiently. Life became more resilient, adapting to extreme cold and low-light conditions that would have been unimaginable in earlier eras. Meanwhile, volcanic activity continued on land and beneath the oceans. Each volcanic eruption released carbon dioxide into the atmosphere. Because the hydrological cycle weakened, this carbon dioxide was not efficiently removed over millions of years. It began to accumulate. As atmospheric carbon dioxide levels rose, the greenhouse effect slowly strengthened. Eventually, levels may have reached hundreds of times higher than present-day concentrations. Only then did the planet begin to warm enough to challenge the frozen equilibrium. Warming initiated the slow retreat of glacial ice. At first, the warming effect was minor, barely noticeable beneath the thick ice sheets. But as the atmosphere trapped more heat, temperatures increased steadily. Thin regions of ice melted, revealing patches of dark ocean. These open waters absorbed sunlight instead of reflecting it, accelerating warming. The feedback loop reversed. Warming melted ice, Melting exposed darker surfaces, and darker surfaces increased warming. Earth began emerging from its icy tomb. As temperatures rose further, the oceans responded. The vast reserves of carbon dioxide dissolved in seawater began to outgas, reinforcing atmospheric warming. The melting ice released trapped gases, further accelerating climate change. Volcanic eruptions continued adding greenhouse gases, helping the atmosphere retain heat. Soon, the planet reached a threshold where ice melted rapidly on a global scale. When Snowball Earth thawed, the transition was explosive. Vast inland glaciers collapsed. Meltwater carved massive channels through the landscape. Catastrophic floods reshaped coastlines. Continents shed enormous amounts of sediment into the oceans, delivering nutrients that would fuel a new wave of biological productivity. The oceans, deprived of sunlight for millions of years, suddenly experienced a surge of photosynthesis as cyanobacteria expanded rapidly into the newly sunlit waters. The release from Snowball Earth triggered dramatic environmental shifts. Oxygen levels began to rise again as photosynthesis accelerated. Nutrient-rich waters stimulated microbial blooms. Carbon cycles restarted. Weathering resumed, stabilizing atmospheric carbon dioxide over time. The planet returned to a more temperate state, capable of supporting a broader range of life. Some scientists believe Snowball Earth episodes occurred more than once. Evidence suggests major glaciations around 2.4 billion years ago, and again between 720 and 635 million years ago. Each event may have been triggered by a combination of biological, geological, and atmospheric feedbacks. Each event dramatically reshaped ecosystems, acting as both a filter and a catalyst for evolution. The aftermath of these global freezes was transformative. Life that survived became stronger, more adaptable, and more capable of innovation. Microbial communities evolved new metabolic strategies. Genetic diversification increased as populations adapted to extreme conditions. Stress-driven evolution accelerated the emergence of new lineages. The harsh conditions favored organisms capable of withstanding fluctuations in temperature, oxygen levels, and chemical environments. Snowball Earth also influenced geological cycles. The massive glaciers scoured continents, grinding rocks into fine sediments. When these glaciers retreated, the sediments washed into the oceans, enriching marine environments. This influx of minerals may have contributed to the rise of more complex life shortly after Snowball Earth episodes. The oceans, once starved of nutrients, became fertile grounds for evolutionary experimentation. Carbon dioxide buildup during global freezes also played a critical role in shaping Earth's climate system. The mechanism of entering a snowball state and escaping it created a natural thermostat, balancing greenhouse gases and temperature extremes. This feedback allowed Earth to maintain long-term habitability despite variations in solar output and continental configurations. Another crucial consequence of Snowball Earth was the strengthening of the ozone layer. Periods of high volcanic activity during and after glaciations released gases that contributed to atmospheric chemistry. With rising oxygen levels, ozone formation increased. This developing ozone shield reduced ultraviolet radiation at the surface, making shallow waters and eventually land more hospitable for future organisms. As the planet warmed fully after each snowball episode, ecosystems rebounded quickly. Microbial mats reoccupied shorelines. Photosynthesis surged. Oxygen levels continued their upward trend. And deep in this recovery, the world inched closer to its next evolutionary milestone, the emergence and diversification of eukaryotic cells. Eukaryotes, complex cells with internal structures, were already present before Snowball Earth, but their expansion may have been slowed by unstable climate and low nutrient availability. After the thaw, environmental conditions improved dramatically. Nutrient-rich oceans, rising oxygen levels, and new ecological niches opened the door for eukaryotic innovation. Many scientists believe the end of Snowball Earth events provided the ecological reset and environmental triggers that allowed multicellular life to flourish. Thus, Snowball Earth, while catastrophic, may have been essential for shaping the future of life. The freezes acted as selective pressures, eliminating fragile lineages and promoting resilient ones. They increased environmental complexity and drove evolutionary creativity. They prepared the planet for the dramatic biological explosions that would follow. By the time Earth fully recovered from its global freezes, the stage was set for a new era. Oxygen levels had climbed, oceans had reorganized, ecosystems had diversified, and eukaryotic cells, once overshadowed by prokaryotes, were ready to rise to dominance. The world that emerged from Snowball Earth was one of resilience, innovation, and renewed possibility. From frozen silence came the conditions for complexity. From a planet locked in ice came the future of life as we know it. After Earth thawed from its global freezes and the climate stabilized, the planet entered a new biological era. For billions of years, prokaryotes had dominated the world, shaping its atmosphere, oceans, and chemical cycles. They were efficient, adaptable, and abundant, but they were also simple. Their small size limited their internal complexity. Their metabolic pathways, though diverse, could only support certain levels of organization. Yet deep within the microbial world, a remarkable evolutionary leap was brewing, one that would forever alter the direction of life on Earth. This leap was the emergence of eukaryotic cells. Eukaryotes are fundamentally different from prokaryotes. They contain a nucleus, the compartment that stores genetic material. They possess internal membranes forming specialized organelles. They have cytoskeletons, structural frameworks that support movement and shape. They conduct complex metabolic processes with far greater efficiency. These innovations allowed eukaryotes to grow larger, evolve new biological strategies, and eventually give rise to multicellular organisms. But their origins lie in a profound event of biological cooperation, the endosymbiotic merger. Endosymbiosis refers to the process by which one organism lives inside another for mutual benefit. In the distant past, some prokaryotic cells engulfed other prokaryotes. Normally, such engulfed organisms would be digested, but in a rare and transformative scenario, the engulfed cell survived. It continued living inside its host, offering metabolic benefits in exchange for protection. These partnerships became permanent, and over millions of years, the engulfed organisms evolved into mitochondria, the energy-producing organelles found in all eukaryotic cells. The origin of mitochondria was crucial. Mitochondria allowed cells to extract energy from food with far greater efficiency through aerobic respiration. This meant eukaryotes could support larger cell sizes, more complex internal structures, and greater genetic material. Mitochondria provided a constant and powerful energy supply that enabled biological innovation on an unprecedented scale. Without mitochondria, the evolution of complex life would have been nearly impossible. The host cell that engulfed the bacteria was likely an archaeon, deepening the biological bond between archaea and bacteria. Modern genetics confirms this ancestry. The nuclear genes of eukaryotes resemble archaeal genes, while mitochondria closely resemble aerobic bacteria. Eukaryotes are therefore hybrids organisms born from the fusion of two ancient worlds. After mitochondria evolved, eukaryotic cells gained the ability to compartmentalize their internal chemistry. Internal membranes folded inward, creating structures like the endoplasmic reticulum and Golgi apparatus. These organelles managed protein folding, transport, and cellular maintenance. With compartmentalization came efficiency, allowing cells to control reactions more precisely. The emergence of the nucleus provided protection for genetic material, reducing the impact of damaging environmental factors like ultraviolet radiation and reactive oxygen species. The cytoskeleton also evolved. This dynamic network of protein filaments allowed cells to change shape, move, and perform complex processes such as phagocytosis, the engulfing of particles. The cytoskeleton enabled internal transport, ensuring that organelles and molecules moved efficiently within the cell. This internal mobility freed eukaryotes from the limitations of diffusion that constrained prokaryotic cell size. Eukaryotes grew larger, more flexible, and more versatile. After Earth's snowball episodes ended, the environment was ideal for the expansion of eukaryotes. Nutrient influx from melting glaciers enriched the oceans. Rising oxygen levels provided the foundation for aerobic metabolism. The planet's climate stabilized, allowing ecosystems to rebound. Eukaryotic cells, equipped with mitochondria, internal membranes, and cytoskeletons, found openings in ecological niches created by the aftermath of global change. Eukaryotes diversified into numerous lineages. Some evolved photosynthetic abilities by engulfing cyanobacteria in another endosymbiotic event. These engulfed cyanobacteria became chloroplasts, the organelles responsible for photosynthesis in plants and algae. Chloroplasts allowed eukaryotes to harness sunlight and produce their own food, expanding their ecological reach into sunlit waters. Like mitochondria, chloroplasts retained traces of their bacterial origins in their DNA, providing strong evidence of their symbiotic past. With both mitochondria and chloroplasts, eukaryotes became engines of biological productivity. Photosynthetic eukaryotes enriched the oceans with oxygen, fueling further evolutionary change. Non-photosynthetic eukaryotes fed on bacteria, algae, and organic matter, forming early food webs. This interplay between producers and consumers marked the beginning of complex ecological networks. Eukaryotic cells also evolved intricate cell cycles, regulating growth and division. They developed sexual reproduction, which allowed genetic recombination between individuals. Unlike the simple binary fission of prokaryotes, sexual reproduction increased genetic variation, fueling rapid evolutionary innovation. This diversity allowed eukaryotes to adapt to new environments, exploit new resources, and withstand changing conditions. For millions of years, eukaryotes remained single-celled, but their internal complexity set the stage for multicellularity. Some eukaryotic cells began forming colonies, living together in coordinated groups. At first, these were loose associations, where each cell remained mostly independent. But over time, cells within colonies developed specialized roles. Some focused on movement, others on feeding or reproduction. The first steps toward multicellular organisms had begun. Yet even before multicellular life emerged, single-celled eukaryotes explored a vast range of ecological roles. They grazed on bacterial mats, swam through sunlit waters, drifted in planktonic clouds, and occupied sediments. Some evolved to be predators, hunting other microorganisms. Others became parasites or symbionts. Single-celled eukaryotes developed locomotion through flagella, cilia, and pseudopodia, displaying behaviors far more dynamic than those of prokaryotes. The evolution of eukaryotes also altered the chemistry of the oceans. Their metabolic activity contributed to the cycling of nutrients, such as nitrogen, phosphorus, and sulfur. They helped shape marine sediments through biomineralization, the production of minerals by living organisms. Some eukaryotes began forming shells or tests made of silica or calcium carbonate. These structures sank to the seafloor after death, creating new types of sedimentary layers that recorded their presence in the fossil record. As eukaryotes spread, they coexisted with prokaryotes, not replacing them, but forming new relationships. Prokaryotes remained the planet's dominant life form in terms of abundance and biomass. They continued driving essential chemical cycles, while eukaryotes added complexity and diversity to ecosystems. Together, they formed the dual foundation of Earth's biosphere. Earth's increasing oxygen levels played a critical role in enabling eukaryotic expansion. Aerobic respiration allowed eukaryotes to support complex internal structures and active lifestyles. Higher oxygen concentrations also supported the evolution of larger cell sizes. While early oxygen levels fluctuated, long-term trends favored organisms capable of exploiting this powerful electron acceptor. Following the emergence of eukaryotes, Earth experienced additional environmental events that continued shaping evolutionary trajectories. Periods of glaciation and warming, shifts in ocean chemistry, and tectonic changes created ecological pressures. Eukaryotes responded with adaptation, speciation, and innovation. Some lineages thrived in sunlit waters, giving rise to early algae. Others specialized in low-oxygen environments, maintaining ancient metabolic strategies. Some evolved in deep sediments away from sunlight. One of the most profound innovations that emerged from eukaryotic evolution was multicellularity. While simple multicellular forms may have existed sporadically earlier, stable multicellular organisms began to appear after eukaryotic cells gained the ability to adhere to one another, communicate chemically, and differentiate into specialized tissues. Multicellularity evolved independently in several groups: fungi, plants, animals, and certain algae. Each lineage followed its own evolutionary path, but all share the advantages of eukaryotic complexity. The emergence of eukaryotic cells was not a single event, but a long evolutionary process shaped by symbiosis, environmental change, and genetic innovation. The merging of archaeal and bacterial lineages created cellular architectures that could support greater complexity. Internal membranes protected genetic material and allowed compartmentalization of biochemical pathways. Mitochondria provided immense energy. Chloroplasts provided photosynthesis. Sexual reproduction generated diversity. Cytoskeletons enabled movement and structural organization. These innovations allowed eukaryotes to transcend the limitations of prokaryotic biology. They could grow larger, move faster, sense their environment more effectively, and process energy with far greater efficiency. This new level of biological sophistication prepared the world for the next major evolutionary transition, the first multicellular organisms. In the wake of Snowball Earth's retreat and the stabilization of climate, eukaryotes diversified rapidly. Fossil evidence from this era includes a variety of enigmatic forms, some resembling simple sponges or colonies of cells. Others formed tessellated patterns in sediments. While the exact identity of many early fossils remains uncertain, they represent experiments in complexity. Evolution was exploring the boundaries of multicellularity long before animals rose to dominance. Eukaryotes also played an important role in oxygen production. Photosynthetic algae increased atmospheric oxygen levels, enabling the eventual expansion of larger and more complex organisms. The oxygenation of deep ocean layers continued slowly, providing habitats suitable for new evolutionary experiments. Environmental fluctuations, including changes in nutrient availability, ocean circulation, and climate, encouraged bursts of innovation and diversification. As eukaryotic lineages expanded, the foundations for the Ediacaran and Cambrian periods were quietly forming. The world was moving toward an explosion of biological diversity unlike anything before. Complex body plans, tissues, organs, and behaviors would soon emerge. But all of these possibilities rested on the existence of eukaryotic cells, the cellular framework capable of building multicellular life. The emergence of eukaryotes marks one of the most transformative events in Earth's history. It is a story of cooperation between species, innovation born from adversity, and the merging of life's ancient branches. It represents the transition from a world of simple cells to a world capable of supporting complex organisms and ecosystems. With eukaryotes established and diversifying, Earth was ready for the next great evolutionary leap, the rise of multicellular life and the strange organisms of the Ediacaran world. The rise of eukaryotic cells marked a turning point in the history of life on Earth. But the next transformation would push biology into entirely new dimensions. For billions of years, life had existed only in microscopic forms, single cells drifting through oceans, clinging to sediments, or living within microbial mats. These cells were diverse and innovative, but each lived alone. Then, in a series of evolutionary steps that unfolded over hundreds of millions of years, some eukaryotic cells began working together. They formed colonies, shared responsibilities, and eventually fused into organisms composed of many cells. This transition, the emergence of the first multicellular life, opened the door to complex bodies, new behaviors, and ecosystems of unprecedented diversity. Multicellularity did not emerge in a single moment or in a single lineage. Instead, it evolved independently multiple times across different groups of eukaryotes in algae, fungi, plants, and animals. But long before these familiar groups appeared, early experiments in multicellularity were taking place in ancient oceans. Simple colonies formed when individual cells failed to separate after division. These clusters gained advantages. They were harder for predators to consume, better able to stay in nutrient-rich waters, and more resistant to environmental stress. Natural selection favored these cooperative groups. In the beginning, these colonies behaved much like their unicellular ancestors. Each cell performed the same functions: capturing energy, processing nutrients, and dividing when conditions allowed. But over time, specialization began to emerge. Some cells focused on movement, using flagella or cilia to propel the colony. Others took on reproductive roles, producing offspring, while non-reproductive cells supported the colony's structure. This division of labor marked a critical step toward true multicellularity. As cell groups grew larger, they required more organization. Chemical signaling evolved, allowing cells to communicate and coordinate activities. These signals regulated growth, reproduction, and differentiation. They enabled cells to respond collectively to changes in their environment. Communication allowed multicellular organisms to behave as unified individuals rather than loose assemblies of cells. With communication came complexity. Early multicellular organisms likely resembled gelatinous sheets, hollow spheres, or simple filaments drifting through shallow waters. They lacked tissues, organs, and symmetry. They moved slowly, if at all, yet they represented something entirely new on Earth. bodies composed of coordinated cells that work together for shared survival. These early forms laid the foundation for future innovations in structure and behavior. The environment played a crucial role in enabling multicellularity. After the Snowball Earth glaciations ended, the climate stabilized. Oceans became richer in nutrients due to massive glacial erosion and runoff. Oxygen levels rose, providing the energy needed to support larger bodies. Chemical gradients in shallow seas, fueled by sunlight and tidal mixing, encouraged metabolic diversity. These conditions created ecological niches ideal for multicellular experimentation. Among the earliest known multicellular organisms were simple algae. Fossil evidence from this period includes red and green algae, some forming filamentous structures, others forming sheets or spherical colonies. These algae performed photosynthesis, contributing further to rising oxygen levels and shaping marine ecosystems. Their multicellular forms were stable and persistent, demonstrating the evolutionary staying power of cooperation. Fungi also began experimenting with multicellularity. Though early fungal lineages remain poorly understood in the fossil record, molecular evidence suggests that simple fungal networks emerged during this period. These organisms may have lived in association with microbial mats, recycling organic material and influencing nutrient cycles. In deeper waters and on the sea floor, other multicellular forms evolved unique strategies. Some formed soft-bodied structures, resembling sponges, porous bodies that allowed water to flow through internal channels. These early sponge-like organisms may represent some of the earliest ancestors of the animal kingdom. They filtered nutrients from seawater, benefiting from the increased oxygen and nutrient availability of post-glacial oceans. These sponge-like creatures lacked nervous systems, muscles, or digestive tracts. But their organization signaled a major evolutionary breakthrough: the ability to build three-dimensional structures composed of different cell types. Their bodies contained specialized cells for feeding, support, and reproduction. They exemplified the earliest stages of tissue differentiation, the hallmark of animal life. As multicellular life spread, ecosystems changed dramatically. Microbial mats, once dominant in shallow waters, encountered competition from multicellular organisms that grazed on them or competed for space. Sediments became richer in organic material as multicellular forms shed cells, secreted mucus layers, and produced metabolic waste. Nutrient cycles intensified, driven by the interactions between unicellular and multicellular organisms. This period also saw the emergence of simple predators. Some multicellular organisms developed the ability to engulf or digest other cells. Although still rudimentary, these predatory behaviors marked the beginning of complex food webs. The presence of predators exerted evolutionary pressure on prey, encouraging defensive strategies such as clustering, hardening cell walls, or developing larger bodies. This predator-prey dynamic fostered innovation and diversification. The exact timing of the earliest multicellular organisms remains debated. Fossil evidence suggests that multicellularity may have begun more than 2 billion years ago, but stable and complex multicellular life became widespread only after 800 million years ago. The Ediacaran Period, beginning around 635 million years ago, marks the first clear appearance of large multicellular organisms in the fossil record. Although the Ediacaran fauna belongs to the next chapter of Earth's history, its roots lie in the early experiments of primitive multicellular forms. As multicellular organisms evolved, they became increasingly specialized. Cells within these organisms communicated through chemical gradients and signaling molecules, ensuring coordination across the body. Some cells became permanent structural components, providing rigidity or flexibility. Others formed protective outer layers. Some specialized in capturing energy through photosynthesis or filtering nutrients from water. Reproductive cells diverged from somatic cells, ensuring the continuity of the organism while allowing for complex body structures. One of the major challenges multicellular organisms faced was the distribution of nutrients and waste. Larger bodies meant that diffusion alone was insufficient for transporting materials. Early organisms developed internal channels or relied on water flow to move nutrients. Sponges, for instance, used pores and canals to direct water through their bodies, capturing food particles in the process. These early transport systems set the stage for circulatory systems that would evolve later in animals. Movement also became more sophisticated. While many early multicellular organisms were sessile, attached to rocks or sediments, others developed simple forms of locomotion. Cilia and flagella coordinated across cells, generating waves that propelled organisms through the water. Coordinated movement required communication between cells, strengthening the evolutionary importance of signaling pathways. Multicellularity also influenced reproduction. Some organisms reproduced by releasing specialized reproductive cells into the water, allowing genetic mixing and increased diversity. Others reproduced asexually by splitting or budding. The combination of reproductive strategies promoted rapid evolution and adaptation. As multicellular life continued to diversify, entire ecosystems formed around these new organisms. Coral-like structures began to emerge, though true corals evolved much later. Mats of multicellular algae covered shallow seafloors, creating layered habitats. Sponge-like animals filtered water, while simple predators explored new ways of hunting. Sediments became more dynamic as organisms burrowed, anchored, or grazed across them. And still, the fossil record from this era remains sparse. Soft-bodied organisms rarely leave behind hard evidence. But the traces that do exist, impressions in sediment, chemical signatures, microfossils, reveal a world in transition. They display swirls, ridges, and patterns representing bodies that lived, grew, and interacted. These patterns demonstrate coordinated cell growth and organized body plans, milestones in the evolution of complexity. Environmental stability played a significant role in this expansion. After the Snowball Earth glaciations, global temperatures moderated, ocean chemistry stabilized with increased oxygenation. Nutrient availability rose dramatically due to erosion and runoff. These changes created fertile conditions for larger organisms to thrive. Multicellularity flourished because the planet provided both the energy and the stability needed for complex life to succeed. The emergence of multicellularity also altered the planet's atmosphere and oceans. Photosynthetic algae increased oxygen production, further oxygenating shallow waters. This oxygenation supported the evolution of aerobic metabolism in multicellular organisms, allowing them to grow larger and more active. As oxygen levels rose, new ecological possibilities opened, paving the way for animal evolution. The first multicellular organisms were simple, but they embodied the essential characteristics that define complex life. They demonstrated division of labor, communication between cells, structural organization, and coordinated reproduction. From these foundations, the animal kingdom would later emerge. Sophisticated tissues, organs, and nervous systems were still far in the future, but the blueprint for complexity was already in place. Even the earliest steps, simple colonies, hollow spheres, soft-bodied structures, signaled an evolutionary direction that would transform the planet. Multicellularity enabled new interactions, new ecological relationships, and new possibilities for adaptation. It marked the end of a world dominated entirely by single cells and introduced the beginning of biological diversity that would eventually fill oceans, land, and sky. By the end of this period, multicellular life had taken root across Earth's oceans. Simple eukaryotic organisms thrived in shallow seas, forming the foundation for more complex forms to evolve. The stage was prepared for the next major chapter in Earth's history, the rise of the Ediacaran organisms, the first truly large and enigmatic multicellular creatures to inhabit the planet. After billions of years dominated by microbes and hundreds of millions of years of experimentation with early multicellularity, Earth entered a strange and extraordinary biological phase. Beginning around 635 million years ago, after the last Snowball Earth glaciers retreated, a new world emerged. A world filled with soft-bodied organisms unlike anything alive today. This era is known as the Ediacaran Period. It marked the first appearance of large, complex life forms visible to the naked eye, yet their bodies, behaviors, and evolutionary relationships remain mysterious. These organisms represented a grand experiment in multicellular life, exploring biological designs that would vanish before the rise of animals as we know them. The Ediacaran seas were warm, shallow, and rich in nutrients. Oxygen levels were rising, currents circulated more vigorously, and sediments carried minerals that fueled biological growth. The oceans were lit by sunlight that penetrated increasingly transparent waters. The planet had emerged from extreme ice ages, and with the thaw came a surge of evolutionary creativity, ecosystems reorganized. New forms spread across the sea floor, creating the first macroscopic landscapes of life. The earliest Ediacaran organisms were unlike any modern creatures. Many had no mouths, no digestive tracts, no muscles, and no recognizable organs. They came in simple geometric shapes: discs, fronds, tubes, ovals, spirals. Some lay flat against the seafloor, others rose like soft, leafy structures anchored in sediment. Their bodies were often quilted or segmented in repeating patterns, as if stitched together from soft compartments. Little evidence remains of their internal anatomy, suggesting that most had simple tissues and relied on diffusion to obtain nutrients and oxygen. One of the most iconic Ediacaran organisms was Dickinsonia. Shaped like an oval mattress with rib-like segments radiating from a central axis, Dickinsonia grew up to 1 meter long, making it one of the first large animals on Earth. Despite its size, it lacked a mouth or gut. It likely absorbed nutrients directly through its underside, living atop microbial mats. As it fed, it left behind footprints, shallow impressions in the sediment that preserve its movements across ancient seafloors. Another notable organism was Rungia, a frond-like creature with delicate branching patterns. It stood upright, like a soft fern anchored in the sediment. Each frond contained intricate vascula, like channels that increased surface area for absorbing nutrients. These patterns suggest a sophisticated method of capturing dissolved organic matter. Like many Ediacaran organisms, Ranger lacked hard parts and left behind only faint impressions in sandstone. Sprigina was another enigmatic form, shaped like a segmented worm, with a crescent-shaped head shield. It has long been debated as a possible precursor to early arthropods. Its bilateral symmetry, a body arranged into left and right halves, hinted at an evolutionary direction that would later dominate animal life. Yet, Sprigina vanished from the fossil record before the Cambrian explosion, leaving behind questions about its true lineage. Frond, like organisms such as Charnia, carpeted the seafloor, forming fields of soft, leaf-shaped bodies anchored like plants. Although they resembled modern sea pens or feather stars, they were structurally different, built from repeated branching modules that defy easy classification. Charnia likely absorbed dissolved nutrients directly from seawater, using its large surface area to maximize intake. Some Ediacaran creatures floated freely. Others attached themselves to microbial mats. Some burrowed shallow impressions into the sediment. Yet few left behind evidence of active movement. The Ediacaran world was not dominated by predators or mobile organisms. Instead, it was a gentle ecosystem where organisms mostly absorbed nutrients, filtered organic particles, or fed on microbial mats that covered the sea floor. The absence of predation created a unique evolutionary environment. Ediacaran organisms could grow soft, broad, and delicate without fear of being eaten. This allowed the evolution of large body sizes and unusual shapes. But it also meant that many Ediacaran innovations were not built for the competitive pressures that would arise later during the Cambrian explosion. The sediments of the Ediacaran world tell a detailed story of these organisms. Microbial mats covered much of the sea floor, forming thick, sticky layers that preserve the impressions of soft-bodied creatures. These mats stabilized sediments and created microenvironments rich in nutrients. Many Ediacaran organisms depended on these mats for food, oxygen, and habitat. The relationship between microbial mats and early macroscopic life was one of the foundational ecological interactions of this period. The Ediacaran experiment also included mobility. Though rare, some organisms developed the ability to move across the sea floor. Cambrian is one of the best examples. It had a soft, slug-like body and a hardened structure at its front that may have functioned like a scraping organ. Cambrian left behind feeding trails that show it grazed on microbial mats, marking one of the earliest known examples of directed feeding behavior. This organism hints at the transition toward more animal-like forms. The rise of mobility introduced new ecological dynamics. Organisms that could move, gained access to new feeding grounds, dominated more space, and avoided competition. These behaviors set the stage for the predatory interactions that would later revolutionize ecosystems during the Cambrian. The Ediacaran environment supported various modes of life: suspension feeders, surface grazers, absorptive organisms, and possibly even early filter feeders. Though diversity was high, ecological interactions remained relatively simple. Competition existed, but predation was minimal. Niches were broad. Organisms coexisted without intense pressure to evolve defensive traits. This peaceful world would soon change. The biological innovations of the Ediacaran period extended beyond body shapes. Some organisms showed evidence of coordinated growth and tissue specialization. Though simple, they represented early versions of developmental processes later refined in animals. For example, the quilted bodies of rangermorphs displayed fractal-like patterns, suggesting regulated growth from modular units. Such growth strategies allowed rapid expansion and efficient nutrient capture. Life in the Ediacaran also expanded vertically. Some organisms grew tall fronds, reaching into higher water columns to access better light or nutrient currents. Others spread broad, leaf-like surfaces across the sea floor. These variations increased ecological complexity, allowing organisms to partition resources more effectively. Spatial structuring. The idea that different organisms occupy different layers or zones began to develop in the oceans. The global distribution of Ediacaran fossils reveals that these organisms lived in diverse environments across multiple continents. Fossil beds in Australia, Russia, Namibia, Canada, and the United Kingdom display similar body plans, suggesting that Ediacaran life spread widely and adapted to a variety of conditions. The worldwide presence of these fossils indicates that Ediacaran ecosystems were interconnected by ocean currents and favorable climate conditions. Another remarkable feature of the Ediacaran period is trace fossils. Though many organisms lacked hard parts, they sometimes left behind tracks, grooves, or tunnels in the substrate. These traces reveal behavior, something fossils rarely capture. Some traces show organisms moving in deliberate paths, suggesting sensory systems capable of detecting chemical or physical cues. Others show evidence of burrowing, which would later become a key ecological innovation. Burrowing allowed organisms to access buried nutrients, oxygenate sediments, and reshape seafloor environments. As the Ediacaran period progressed, environmental changes began altering ecosystems. Oxygen levels continued to rise, nutrient availability fluctuated, sea levels shifted due to tectonic movements. Microbial mats, once widespread, began to decline in some regions as burrowing organisms disrupted their structure. This disruption marked the beginning of bioturbation, the mixing of sediments by living organisms. Bioturbation changed the chemistry and stability of sediments, impacting organisms that relied on microbial mats. Some Ediacaran organisms adapted to these changes. Others could not. The decline of microbial mats reduced the habitat and food source for many mat-dependent species. The emergence of more mobile and active organisms introduced competition. New behaviors, such as grazing and burrowing, reshaped the ecosystem. Although the Ediacaran experiment produced remarkable diversity, it was fragile, dependent on environmental stability and low predation pressure. Toward the end of the Ediacaran, extinction waves began affecting these organisms. The exact causes remain uncertain. Possibilities include climatic fluctuations, ocean chemistry shifts, rising predation from newly evolving animals, and ecological competition. What is clear is that many Ediacaran lineages vanished completely before the Cambrian period began. Their disappearance opened ecological space for the dramatic biological explosion that would follow. The Ediacaran experiment was a unique moment in Earth's history, a period when life explored forms and strategies that have no modern parallels. Though few Ediacaran organisms gave rise directly to modern animals, the period provided essential evolutionary groundwork. It demonstrated that multicellularity could produce large bodies, complex shapes, and coordinated behaviors. It tested developmental pathways, ecological roles, and structural possibilities. The Ediacaran world was a canvas of soft life, painted with fronds, discs, segmented ovals, and quilted forms. It was a quiet world, free from predation, dominated by gentle feeding strategies and slow movements. But it was also a world preparing for transformation. Beneath the surface of these soft-bodied experiments, evolutionary mechanisms were gearing up for the next chapter, a chapter defined by innovation, arms races, and rapid diversification. As the Ediacaran period came to a close, the stage was set for one of the most extraordinary events in the history of life, the Cambrian explosion. After the quiet, soft-bodied world of the Ediacaran came one of the most dramatic turning points in the history of life on Earth. Around 541 million years ago, biological innovation accelerated at a pace never seen before. Ecosystems transformed, new body plans emerged, predators burst onto the scene. Shells and skeletal structures appeared for the first time. Life diversified into nearly every major animal group known today. This extraordinary moment is called the Cambrian explosion, not an instant event, but a rapid geological interval during which complexity flourished and the foundations of modern animal life were established. The Cambrian seas were warm, shallow, and filled with oxygen. Tectonic activity created extensive continental shelves bathed in sunlight. Nutrient-rich runoff flowed into oceans, stimulating productivity. Rising oxygen levels allowed organisms to grow larger and develop energy-demanding tissues such as muscles, nerves, and circulatory systems. The biological and environmental conditions aligned perfectly for evolutionary experimentation. One of the defining features of the Cambrian explosion was the sudden appearance of hard parts: shells, exoskeletons, spines, and teeth. These structures provided protection from predators, support for movement, and new ways of interacting with the environment. The fossil record from this time is rich because these hard parts preserved well, capturing the details of organisms that would otherwise have disappeared without a trace. Trilobites became some of the most iconic inhabitants of the Cambrian seas. These arthropods possessed segmented bodies, jointed legs, and hard exoskeletons. They crawled across the seafloor, burrowed in sediments, or swam gracefully through the water. Trilobites developed compound eyes made of calcite, some of the earliest and most sophisticated visual systems in the animal kingdom. Their diversity exploded, producing hundreds of species with unique shapes and behaviors. Trilobites represent the power of adaptation during this era, flourishing across varied environments. Another remarkable creature was Anomalocaris, often considered the first apex predator. It grew up to a meter long, a giant of its time. With large compound eyes, a flexible body, swimming lobes, and ring-shaped jaws lined with hard plates, Anomalocaris hunted trilobites and other prey with precision. Its rise signaled a major shift in ecosystem dynamics. The presence of predators introduced evolutionary pressure, driving prey to develop defenses such as armor, burrowing behaviors, and escape strategies. Hallucigenia, a small but bizarre organism, walked on spindly legs while sporting long dorsal spines for protection. Its unusual appearance puzzled scientists for decades, but it represents the experimentation of the Cambrian, a time when life tested biological designs that sometimes bordered on the surreal. The Cambrian explosion introduced diverse body plans known as phyla, the highest major groups in animal classification. Many modern phyla emerged during this time, including arthropods, mollusks, annelids, echinoderms, brachiopods, chordates, and cnidarians. Each phylum represents a distinct blueprint of body organization. These blueprints, once established, persisted for hundreds of millions of years and still define animal diversity today. One of the most significant developments during the Cambrian was the evolution of the chordates, the group that includes fish, amphibians, reptiles, birds, mammals, and eventually humans. Early chordates such as Picaia and Hycoichthys possessed flexible rod-like structures called notochords, which supported their bodies and allowed undulating swimming motions. They also had segmented muscles, primitive nervous systems, and early versions of gill structures. Though small and simple, these ancestors marked the beginning of a lineage that would dominate vertebrate evolution. The Cambrian seas teemed with brachiopods, shelled filter feeders resembling clams and mollusks, including early snails and soft-bodied ancestors of squids. Echinoderms, distant relatives of modern starfish, appeared in primitive forms with radial symmetry, Cnidarians, the group that includes jellyfish and corals, diversified into new shapes and sizes. Burrowing behaviors became widespread during the Cambrian. Organisms dug into sediments for protection or to access buried food sources. These burrows transformed seafloor environments, oxygenating sediments and altering chemical cycles. Bioturbation, the mixing of sediments by living organisms, reached new levels, impacting nutrient availability and reshaping ecosystems. Skeletonization was a major evolutionary innovation. Organisms began secreting calcium carbonate or calcium phosphate to build shells and protective structures. The availability of minerals in seawater facilitated this process. Skeletons allowed for greater mobility, structural support, and predator resistance. They also created new ecological opportunities, such as reef building and complex habitat formation. The Cambrian explosion was fueled not only by external environmental change, but also by internal genetic developments. One of the most important innovations was the evolution of Hox genes, master regulatory genes that control the layout of body plans. Hox genes guide the formation of segments, limbs, organs, and overall body structure. Once these genes evolved, they enabled rapid diversification, because small genetic changes could produce significant differences in anatomy. This flexibility accelerated evolution, allowing organisms to explore a vast range of body designs. Ecological interactions also drove diversification. Predator-prey, arms races created selective pressures that encouraged rapid adaptation. Predators evolved better senses, mobility, and weapons, while prey evolved armor, camouflage, and defensive strategies. Competition for food and space encouraged organisms to occupy new niches, leading to the diversification of species and ecological roles. The Cambrian seas grew increasingly complex. Reefs formed from early sponges and coral-like organisms, creating three-dimensional habitats. Planktonic organisms drifted through sunlit waters, forming the base of food chains. Scavengers roamed the sea floor, feeding on organic debris. Filter feeders pumped water through specialized structures, capturing suspended particles. Predators patrolled the middle waters. Every layer of the ocean became an arena for life, filled with interactions and behaviors that defined ecological communities. Soft-bodied organisms that had dominated the Ediacaran world declined dramatically. Some were outcompeted by more active, armored Cambrian animals. Others could not survive the rise of predators. As ecological pressure intensified, the gentle Ediacaran world faded, replaced by a dynamic and often violent ecosystem shaped by competition and survival. Major fossil sites, such as the Burgess Shale in Canada and the Chengjiang Formation in China, provide exquisite snapshots of Cambrian life. Their exceptional preservation reveals detailed anatomy of soft-bodied organisms, offering rare insights into the diversity of ancient ecosystems. Creatures preserved in these deposits include Opabenia with 5 eyes and a proboscis-like appendage, Wywaxia covered in protective scales, and Morella, a delicate arthropod with intricate spines. These fossils display the experimental nature of evolution during the Cambrian, a period when evolution seemed to invent new designs with extraordinary freedom. As the Cambrian period progressed, ecosystems stabilized somewhat. The rapid burst of new body plans slowed, and many experimental forms vanished. The major phyla solidified into recognizable lineages that would persist for hundreds of millions of years. The world had transitioned from a planet dominated by microbial mats and soft-bodied organisms to one filled with armored predators, burrowing creatures, and complex food webs. This transformation set the stage for future evolutionary advancements. Oxygen levels continued to rise, supporting larger body sizes and more active lifestyles. Nutrient cycles intensified, driven by biological activity. Tectonic processes reshaped oceans and coastlines, influencing habitats and promoting further diversification. Evolutionary innovation continued, but the foundational explosion of body plans had already established the blueprint for future life. The Cambrian explosion was not merely a moment of rapid evolution, it was a permanent shift in the trajectory of life. Every animal on Earth today traces its ancestry to creatures that first appeared during the Cambrian. The basic structures of eyes, limbs, digestive systems, muscles, nerves, and circulatory networks were all established during this time. The architecture of life became increasingly modular, allowing new adaptations to arise through variations on established themes. The presence of predators for the first time changed the behaviors of organisms dramatically. Hiding, burrowing, swimming, camouflage, and hard shells all emerged as responses to predation. Ecosystems became dynamic rather than static. The Cambrian explosion transformed oceans into complex arenas of interaction, innovation, and survival. By the end of the Cambrian, the stage was set for further developments in animal evolution. The earliest vertebrates were poised to rise. Ecosystems became more interconnected. Marine life grew more sophisticated. Plants and fungi were preparing for their eventual colonization of land. The Cambrian explosion had created the biological foundation upon which all future life would build. It was a turning point, a moment when Earth shifted from simple multicellularity to a world of predators, prey, shells, eyes, limbs, and breathtaking diversity. Evolution had taken a bold leap forward, and nothing would ever be the same. After the Cambrian explosion reshaped the living world with predators, hard shells, complex body plans, and dynamic ecosystems, the oceans entered a new era of biological expansion. During the Ordovician and Silurian periods, life did not simply diversify, it spread into every corner of the seas. New ecosystems emerged in deep waters, on continental shelves, and within reef systems flourishing in warm, sunlit shallows. Marine life became more structured, more interconnected, and more complex. The oceans transformed into vast theatres of evolution, where countless organisms explored new strategies for feeding, moving, defending, and reproducing. In the Ordovician seas, trilobites remained abundant, but they were no longer the sole dominant group. Brachiopods, with their hinged shells, flourished on seafloors, attaching themselves to rocks or soft sediments. Some developed long stalks that lifted their shells above the substrate, accessing nutrient-rich currents. Bryozoans, colonial organisms that built intricate lattices of calcium carbonate, spread across seafloors like living carpets. These colonies created structured habitats that sheltered small organisms, contributing to the complexity of marine environments. Coral-like organisms also began building reefs, forming barriers and platforms that reshaped coastlines. While these early reefs were not dominated by true corals, they provided similar ecological roles. Reefs supported fish-like creatures, arthropods, mollusks, and countless invertebrates. They created shelter, feeding grounds, and nurseries. As these ecosystems expanded, the complexity of interactions between species grew dramatically. Cephalopods, distant relatives of modern squids and octopuses, became formidable predators of the Ordovician seas. Some developed long, straight shells, while others evolved coiled shells for better mobility. These cephalopods used jet propulsion to move swiftly, hunting trilobites and soft-bodied prey. Their rise marked a new level of sophistication in predatory behavior. They had sharp beaks, powerful tentacles, and keen sensing abilities. For the first time in Earth's history, ocean predators were not just opportunistic hunters, but intelligent, adaptable, and versatile. The Ordovician period also saw major advancements in jawless fish. Though they lacked jaws, these early vertebrates, known as agnathans, possessed cartilaginous skeletons, gill structures, and primitive sensory systems. They filtered particles from the seabed or scavenged organic matter. Some developed bony armor plates on their heads and bodies, providing protection against predators. This early armor would later influence the evolution of bony fish and armored aquatic vertebrates. As life expanded in the oceans, primary productivity increased significantly. Plankton, tiny drifting organisms, flourished in sunlit upper waters. Phytoplankton performed photosynthesis, producing vast amounts of oxygen and forming the base of marine food webs. Zooplankton fed on phytoplankton, providing prey for larger organisms. This planktonic boom supported the expansion of predators at every level, from tiny crustaceans to giant cephalopods. The Ordovician oceans were rich in biodiversity, but they also experienced profound environmental change. Plate tectonics shifted continents and opened new ocean basins. Sea levels rose and fell. Volcanic activity altered atmospheric composition. One of the most significant geological events of the time was the formation of the Appalachian Mountains, whose erosion enriched oceans with minerals that fueled life. These environmental changes shaped ecosystems, driving evolutionary innovation and diversification. Yet this dynamic age ended abruptly. Around 444 million years ago, the Ordovician-Silurian mass extinction struck, eliminating nearly 85% of marine species. Likely triggered by a combination of global cooling, glaciation, and falling sea levels, this extinction drastically reshaped marine life. Shallow seas disappeared as ice sheets expanded, destroying habitats. Organisms adapted to warm waters struggled to survive, trilobites suffered major losses, and many brachiopods, bryozoans, and reef builders vanished. But extinctions, while devastating, often open ecological opportunities. Survivors evolved rapidly in the aftermath, rebuilding ecosystems during the Silurian period. As Earth warmed again, sea levels rose, flooding continental shelves. New reef systems formed, now dominated by organisms more similar to modern corals. These reefs teemed with life, serving as hotspots of evolution. During the Silurian, fish underwent major evolutionary advancements. Jaws evolved a breakthrough that transformed vertebrate biology. Early jawed fish, known as placoderms, developed armored plates on their heads and thoraxes. Their jaws allowed them to bite, crush, and manipulate prey with far greater control than jawless fish. This innovation opened new feeding strategies, from active predation to the consumption of hard-shelled organisms. The evolution of jaws was one of the most significant steps in vertebrate evolution, setting the stage for sharks, rays, and eventually land vertebrates. Cartilaginous fish, the ancestors of modern sharks, also began emerging. Early forms had streamlined bodies, paired fins, and powerful tails. They were agile predators, hunting fish and invertebrates with increasing speed and precision. Their development marked the birth of true piscine predators capable of dominating marine ecosystems. Bony fish, another major vertebrate lineage, also appeared during this time. Unlike cartilaginous fish, bony fish developed internal skeletons made of bone. They evolved swim bladders, internal gas-filled organs that allowed them to control buoyancy. This adaptation enabled them to inhabit deeper waters, hover effortlessly, and maneuver with precision. The rise of bony fish diversified marine vertebrate ecosystems further. Marine plants and algae continued spreading across coastal regions. Photosynthetic organisms expanded their range, growing in shallow waters and creating oxygen-rich habitats. These zones supported grazing organisms, filter feeders, and predators, forming early versions of modern coastal ecosystems. Arthropods also diversified. Eurypterids, giant sea scorpions, became some of the top predators. Some eurypterids grew over 2 meters long, with powerful claws, segmented bodies, and armored exoskeletons. Their dominance in shallow seas demonstrated the competitive intensity of marine life. Other arthropods, such as early crustaceans, scuttled across seafloors or swam through water columns, feeding on detritus, plankton, or small fish. As life flourished, ecosystems grew increasingly interconnected. Predators influenced prey populations. Prey shaped predator evolution. Coral reefs created refuges for smaller organisms, encouraging biodiversity. Sediment burrowers, oxygenated seafloors, filter feeders cleaned water and redistributed nutrients. Every organism contributed to a web of interactions that supported the entire marine environment. By the late Silurian, the oceans had become highly complex. Reef systems expanded across tropical regions. Vertebrates diversified rapidly. Arthropods evolved new forms. Plankton productivity remained high. Earth's marine ecosystems were vibrant, dynamic, and filled with evolutionary experimentation. One of the most profound consequences of oceanic diversification was the gradual emergence of organisms capable of exploring environments beyond water. Plants and algae began colonizing damp shorelines. Arthropods ventured onto tidal flats, breathing air through simple respiratory structures. Fish developed stronger fins and internal systems that would one day allow them to crawl onto land. Though the conquest of land belongs to later chapters, it began with the innovations forged during the ocean's golden age. The oceans of this era were not just habitats, they were evolutionary engines. New sensory systems evolved, including primitive lateral lines in fish that detected water movement. Eyes became more refined across many lineages. Nervous systems grew more complex. The evolution of jaws revolutionized feeding. Fins evolved into structures capable of finer control. Respiratory systems became efficient at extracting oxygen from water. Reefs, in particular, became centers of innovation. They offered shelter, competition, and varied resources. Organisms developed camouflage, mimicry, and predatory strategies. Some evolved symbiotic relationships with algae or bacteria. These interactions drove diversification, reinforcing the role of reefs as evolutionary hotspots. The conquest of the oceans also shaped Earth's climate. Photosynthetic organisms continued producing oxygen, gradually increasing atmospheric levels. Marine life helped regulate carbon dioxide by sequestering carbon in shells and sediments. Over time, these processes stabilized climate patterns, influencing everything from ocean circulation to atmospheric chemistry. Mass extinctions punctuated this era, each reshaping ecosystems and opening opportunities for survivors. Each recovery period brought bursts of evolutionary innovation. Life in the oceans displayed resilience and adaptability, continually evolving in response to environmental challenges. By the end of this chapter, the oceans had become unrecognizable compared to their early days. What began as simple microbial environments had transformed into dynamic kingdoms of fish, arthropods, mollusks, cephalopods, corals, and countless other organisms. The foundations of modern marine biodiversity were firmly in place. But evolution was not finished expanding its reach. Soon, life would take one of its most dramatic steps, leaving the oceans and venturing onto land, reshaping the planet forever. For billions of years, Earth's landmasses were barren landscapes of rock, sand, and volcanic debris. Continents were shaped by tectonics, carved by wind and water, and sculpted by long eras of geological activity. But no green life yet covered the surface. Everything above the shorelines was empty. The only signs of water-driven erosion came from rain and rivers. The only colors came from minerals and weathered stone. But during the Silurian and early Devonian periods, a profound transformation began. Life, which had thrived in the oceans, made a bold leap onto land, and the first pioneers to reshape the continents were plants.